This object should not be possible. 12 miles wide, 2 times the mass of the Sun, a magnetic field so strong it rips apart the fabric of empty space. And on December 27, 2004, one of them screamed across the galaxy with a burst of energy that outshone 100,000 years of sunlight in 1/10 of a second. This is not a black hole, it is something stranger. Scientists call them Magnetars, dead stars, cosmic corpses left behind when something massive collapses so violently that atoms themselves are crushed into oblivion. But where black holes hide their violence behind an event horizon, Magnetars do their damage out in the open. They warp reality, they twist the vacuum. They release more energy in a fraction of a heartbeat than our Sun will produce across geological epochs. And unlike the singularities we have learnt to fear from a comfortable distance, Magnetars can reach across light years and touch you. For decades, astronomers observed bursts they could not explain, gamma rays that repeated, X-ray sources that pulsed with no clear power supply, phenomena that broke every model of how neutron stars were supposed to behave. And then in 1992, 2 physicists proposed something radical. What if some neutron stars are born with magnetic fields 1,000 trillion times stronger than Earth's? What if the rules we thought governed these objects simply did not apply? What followed was not a neat confirmation. It was a slow, uncomfortable realization that the universe had been hiding something from us. Something spinning in the dark, something that bends the laws of physics until they scream. This is the story of Magnetars, the most extreme magnets in existence, the brightest bursts ever recorded, and the moment when impossible became observed fact. Welcome to Magnetic Space. If you're new here, please subscribe. We make these documentaries every day, and honestly, we'd love to have you along for the ride. Before we begin, tell us in the comments where you're watching from and what time it is there. Now settle in. This is going to be a good one. The universe has a graveyard. It isn't marked with headstones or mourners dressed in black. There are no eulogies, no flowers laid carefully across cold earth. The cosmic graveyard exists at a scale so violent and so incomprehensibly bright that when something dies there, the explosion can outshine entire galaxies for weeks. And what gets left behind after the light fades is stranger than the death itself. Every star you have ever seen in the night sky is burning. Not burning the way a campfire burns, consuming wood and oxygen. Stars burn through nuclear fusion, crushing hydrogen atoms together in their cores with such force that they merge, release energy, and keep the star from collapsing under its own weight. It's a balance. Gravity wants to crush everything inward. Fusion pushes back. For most stars, that balance lasts billions of years. Our Sun has been running this trade-off for about 4.5 billion years and has another 5 billion or so left in the tank before the fuel runs out. Massive stars don't get that luxury. If you're born with more than about 8 times the mass of our Sun, your life is short, brutal, and spectacular. The extra mass means stronger gravity pulling inward, which means you need to burn hotter and faster to hold yourself up. A star 8 times the Sun's mass might only last 20 million years. A star 25 times the Sun's mass might burn through its fuel in just a few million years. In cosmic terms, that's a blink. Humans have been anatomically modern for longer than some of these stars have existed. But while they last, they burn with ferocious intensity. They're not just fusing hydrogen into helium the way our Sun does. They move through the entire periodic table like a checklist. First hydrogen to helium, then helium to carbon, carbon to oxygen. Oxygen to neon, neon to magnesium, magnesium to silicon, silicon to iron. Each stage produces less energy than the one before it. Each stage runs faster. The hydrogen burning phase might take millions of years. The final stage, fusing silicon into iron in the core, takes about 1 day. 1 day, 24 hours, to build an iron core at the center of a star the size of a small solar system. And then the star hits a wall it cannot climb. Iron is the endpoint. Fusing iron doesn't release energy, it costs energy. Once the core is made of iron, there is no more fuel, no more outward pressure. Gravity, which has been held at bay for millions of years by the furnace at the star's center, finally wins. And when gravity wins at this scale, it doesn't ease the star into retirement. It crushes the core in about 1 second. The collapse happens so fast that the outer layers of the star don't even know it started. The core, a ball of iron roughly the size of Earth, containing more than 1 solar mass, implodes. Electrons get smashed into protons, turning them into neutrons and releasing a flood of ghostly particles called neutrinos. The collapse only stops when the core reaches nuclear density, the point where neutrons themselves refuse to be compressed any further. The core bounces. That bounce sends a shock wave tearing back outward through the collapsing star, ripping it apart from the inside. What you see from the outside is a supernova. 1 star for a few weeks, shining as brightly as 100 billion stars. If a supernova went off within a few dozen light years of Earth, the burst of radiation would strip our atmosphere and sterilize the surface. We would be gone before anyone understood what was happening. Fortunately, there are no candidates that close. The nearest massive star capable of going supernova is probably Betelgeuse, sitting about 550 light-years away in the constellation Orion. When it goes, and it will go someday, possibly tomorrow, possibly in 100,000 years, it will be visible in daylight. You will be able to see it during the afternoon, a second sun hanging in the sky. It will not hurt us, but it will be impossible to miss. Supernovae are the reason you exist. Every atom in your body, heavier than hydrogen, was forged inside a star. The carbon in your cells, the oxygen you breathe, the calcium in your bones, the iron in your blood, all of it was made in the core of a massive star and scattered across space when that star exploded. The universe started with hydrogen and helium. Everything else had to be built. Supernovae are the construction sites. They're violent, yes, but they're also generous. They seed the galaxy with the raw material for planets, oceans, and eventually biology. But we're not here to talk about what the supernova throws outward. We're here to talk about what it leaves behind. When the core of a massive star collapses and bounces, what remains is no longer a star in any recognizable sense. It's a ball of neutrons. Neutrons packed so tightly that a single teaspoon of the material would weigh about 1 billion tons on Earth. The object is called a neutron star, and it is one of the strangest things the universe produces outside of a black hole. Neutron stars are small, absurdly small for something containing more mass than the Sun. The typical neutron star is about 12 miles across, 20 kilometers if you prefer metric. You could fit one comfortably inside the city limits of a mid-sized metropolitan area. Los Angeles is wider than a neutron star, so is London, so is Tokyo, and yet that city-sized ball of neutrons weighs about 1.4 times what our entire sun weighs. Let that settle for a moment. Take the sun. Take all of its mass, all of its light, all of its heat, all of the gravity that holds 8 planets and countless smaller bodies in orbit around it. Compress that mass down until it fits inside a sphere you could drive across in 20 minutes. That is what a neutron star is, a dead star. A remnant, the densest stable object in the universe that isn't a black hole. The density is so extreme that the physics governing neutron stars operates at the edge of what we understand. The mean density of a neutron star is around 10 to the 14th times the density of water. That number is not a metaphor. It is a measured, calculated fact. Matter at that density behaves in ways we can only approximate with our best models, and even then, we're guessing at the details. The core might contain exotic particles we have never observed in a laboratory. The crust is thought to be made of a lattice of iron nuclei, so tightly packed that it makes diamond look like styrofoam. Below that, a liquid of neutrons. Below that may be quark matter, where neutrons themselves break apart into their constituent pieces. We don't know. We can't go there. We can't build a neutron star in a lab. All we can do is watch them from a distance and try to reverse engineer the rules. Most neutron stars are born spinning. The collapsing core conserves angular momentum, so if the original star was rotating even slowly, the neutron star that forms will rotate very fast, hundreds of times per second in some cases. And because neutron stars have intense magnetic fields threading through them, that rotation turns them into cosmic lighthouses. Beams of radiation sweep across space like searchlights. If one of those beams happens to point toward Earth, we see a pulse, a regular tick, like a clock. Astronomers call these objects pulsars, and we've known about them since 1967, when Jocelyn Bell Burnell discovered the first one, and briefly wondered if she'd picked up a signal from an alien civilization. She hadn't. It was just a neutron star doing what neutron stars do. Spinning, beaming, ticking away in the dark. Pulsars are strange enough, but they are not the strangest thing a neutron star can be. In the early 1990s, astronomers started noticing certain neutron stars that didn't behave like the others. They emitted sudden, enormous bursts of X-rays and gamma rays, explosions of energy so powerful that they could be detected from thousands of light years away. These bursts were not predictable. They didn't follow the steady rhythm of a pulsar. They were violent, erratic, and far too energetic to be explained by the rotation and radiation mechanisms that powered ordinary pulsars. The objects producing these bursts were given a name, Magnetars. The name is shorthand for magnetic star, and it is the single most appropriate label in all of astronomy. Because what makes a magnetar different from a regular neutron star is its magnetic field, not just stronger, incomprehensibly stronger. A typical pulsar has a magnetic field about 1 trillion times stronger than Earth's. That alone is enough to rip the iron out of your blood if you got close enough. A magnetar's magnetic field is another 100 to 1,000 times stronger than that. We're talking about magnetic fields in the range of 10 to the 15th Gauss. For context, the strongest sustained magnetic field ever created in a laboratory on Earth is about 45 Tesla, which converts to about 450,000 Gauss. A magnetar's field is roughly 10 billion times stronger than that. At those field strengths, physics breaks. Atoms get stretched into elongated shapes. Light itself bends. The vacuum of space near a magnetar becomes birefringent, meaning it splits light into two different polarizations the way certain crystals do on Earth. The magnetic field is so intense that it warps the structure of space-time in ways that only black holes are supposed to manage. And the energy contained in that magnetic field is staggering. Estimates suggest that a magnetar's magnetic field holds about the same amount of energy as our sun will emit over the course of 100,000 years. 100,000 years of sunlight, compressed into the magnetic field threading through a sphere 12 miles wide. That energy doesn't just sit there quietly. It leaks out, it twists. It causes starquakes, where the neutron star's crust cracks under the stress, releasing bursts of radiation so bright they can be seen across the galaxy. Nobody knows exactly how magnetars form. That has been one of the central puzzles in astrophysics for more than 2 decades. Regular neutron stars are born with strong magnetic fields simply because the collapsing core compresses and amplifies whatever magnetic field the original star had. But that process alone doesn't explain magnetars. You can't get to 10 to the 15th Gauss just by collapsing a normal massive star. Something else has to happen. The leading idea involves rotation. If the progenitor star is spinning very rapidly when it collapses, the newly formed neutron star inherits that rotation and spins even faster due to conservation of angular momentum. In the chaotic first few seconds after the bounce, while the core is still partly fluid and extremely hot, a dynamo effect can kick in. Convective motions and rapid rotation work together to amplify the magnetic field far beyond what compression alone would produce. Think of it like a cosmic blender, stirring and twisting magnetic field lines until they reach absurd strengths. The catch is that not every collapsing massive star is rotating fast enough to trigger that dynamo. Most are not, which is why magnetars are rare. Current estimates suggest that only about 1 in 10 core collapse supernovae produces a magnetar. The rest produce ordinary neutron stars, which are still extraordinary objects, just not magnetars. For a star to be rotating fast enough at the moment of collapse, something usually has to spin it up ahead of time. One way that happens is in binary systems, where a massive star has a companion. The two stars can interact, transferring mass and angular momentum, spinning each other up in a slow gravitational dance that lasts millions of years. When the more massive star finally collapses, it's rotating fast enough to birth a magnetar instead of a regular pulsar. Another possibility is that the progenitor star was just born rotating rapidly, a consequence of the turbulent cloud of gas it formed from. Either way, the conditions have to be just right. In early 2026, astronomers reported the first direct observation of a magnetar being born. They had been watching a supernova, tracking its light curve, measuring its spectrum, when the telltale signs of a newborn magnetar began to emerge from the fading explosion. The light didn't fade the way it should have. It stayed brighter than expected, powered by energy leaking out of a rapidly spinning, hypermagnetized neutron star buried at the center of the debris. It was the first time anyone had caught the process in the act. For years, magnetars had been theoretical consequences of rare conditions. Now we had watched one wake up. The universe, it turns out, has been making these things for as long as it has been making stars. Magnetars are thought to be relatively young objects, at least the active ones. The intense magnetic field decays over time, bleeding energy into space. After about 10,000 years, most magnetars have quieted down enough that they stop producing the dramatic bursts that make them detectable. They don't vanish. They just fade into the background population of neutron stars, their magnetic fields still strong, but no longer violent. If that timeline is correct, then the magnetars we see today are the freshest remnants of the cosmic graveyard. The bodies are still warm. What remains unclear is whether the process that creates a magnetar is fundamentally different from the process that creates a regular neutron star, or whether it's just a matter of degree. Is there a sharp boundary between the two, or is there a continuum? Can a neutron star born with a moderately strong magnetic field somehow evolve into a magnetar, or is the die cast in the first second after the core bounces? These are not abstract questions. They shape how we understand stellar evolution, how we model supernova mechanics, and how we predict what kinds of objects should exist in galaxies near and far. We know the ingredients now. A massive star, at least 8 times the Sun's mass, a core that collapses in under a second, a bounce that triggers a supernova. And if the conditions are right, if the star was spinning fast enough, if the dynamo kicked in during those first chaotic moments, a magnetar, a neutron star with a magnetic field strong enough to rewrite the rules of physics in its immediate neighborhood. An object 12 miles wide containing more mass than the Sun and wrapped in a magnetic field holding 100,000 years of solar energy. And the strangest part is that these things are not sitting quietly in the dark. They are active, they are violent, they produce bursts of radiation so powerful that they have been detected from halfway across the observable universe. One burst, lasting 1/10 of a second, can release more energy than our Sun will produce in 200,000 years. We're just beginning to understand what that means. The first cracks in the standard story appeared quietly. Nobody rings a bell when physics stops making sense. There's no alarm that goes off in an observatory control room when an object in space refuses to follow the rules. The warning signs show up as small inconsistencies buried in data, strange readings that don't quite match what the textbooks say should happen. And for a long time, those inconsistencies get ignored because ignoring them is easier than admitting the model might be wrong. In the late 1970s and early 1980s, astronomers began detecting a class of objects that didn't fit. They called them soft gamma repeaters, or SGRs, and the name itself is a placeholder, the kind of label you slap on something when you have no idea what it actually is. Soft, because the gamma rays they emitted were on the lower energy end of the gamma spectrum. Repeaters, because they kept bursting over and over from the same location in the sky. The first one showed up on January 7, 1979. Satellites orbiting Earth, designed to monitor nuclear weapon tests by detecting gamma-ray bursts, picked up a signal unlike anything they had seen before. It came from deep space, from a fixed point in the constellation Sagittarius. The burst lasted a few tenths of a second, and then it happened again a few weeks later, and again, and again. Over the course of several years, the object, now catalogued as SGR 1806-20, produced dozens of short, sharp bursts of gamma rays. Each burst released an enormous amount of energy, but not quite as much as a traditional gamma ray burst, the kind produced when a massive star collapses into a black hole. These were smaller, softer, and they repeated. Gamma-ray bursts don't repeat. Whatever this was, it was something else. Then, in 1981, astronomers identified another strange class of objects. These were called anomalous X-ray pulsars, or AXPs. The name, again, is a confession of ignorance. Anomalous because they didn't behave the way pulsars were supposed to behave. Most pulsars are powered by rotation. They spin rapidly, hundreds of times per second in some cases, and the energy for their radiation comes from that spin gradually slowing down. It's a simple trade. Rotational energy converts into radiation. The pulsar slowly bleeds its spin into space, and eventually, millions of years later, it winds down and goes quiet. AXPs didn't follow that script. They pulsed, yes, sending out regular ticks of X-ray radiation just like a normal pulsar. But they were spinning too slowly to account for the amount of energy they were radiating. A typical AXP might complete one full rotation every 5 to 12 seconds. That's glacial by pulsar standards. And yet these objects were pumping out X-rays at a rate that should have required them to be spinning hundreds of times faster. The math didn't work. If you tried to power an AXP the way you power a normal pulsar, you ran out of energy almost immediately. The rotation couldn't supply enough juice. So where was the energy coming from? For more than a decade, nobody had a good answer. Some astronomers suggested the AXPs might be accreting material from a companion star, pulling gas inward and heating it to X-ray temperatures. That model works for certain binary systems, but observations kept failing to find evidence of companions around most AXPs. Others proposed that maybe these were just ordinary pulsars seen from an unusual angle, or that there was some exotic mechanism involving fallback material from the supernova that created them. None of the explanations held up cleanly. Every model introduced more problems than it solved. By the end of the 1980s, astronomers had catalogued a small but growing list of SGRs and AXPs. The objects were rare, scattered across the galaxy, and every single one of them was a puzzle. They looked like neutron stars. They had the right masses, roughly 1.4 solar masses. They had the right sizes, a few dozen kilometers across. They pulsed. They emitted high-energy radiation. They sat in the remnants of supernova explosions. But they didn't behave like neutron stars were supposed to behave. They were too bright, too slow, too energetic, and way too strange. Then in 1992, two physicists published a paper that changed the conversation. Robert Duncan, then at the University of Texas at Austin, and Christopher Thompson at the University of North Carolina, proposed a new model. They didn't try to fix the existing neutron star framework. They threw it out and built something else. Their idea was simple, radical, and as it turned out, correct. What if some neutron stars were born with magnetic fields so strong that the magnetic energy alone could power the radiation for thousands of years? What if the source of energy in SGRs and AXPs wasn't rotation at all, but magnetism? The paper appeared in the Astrophysical journal Letters, and it introduced a term that would eventually become one of the most evocative in all of astronomy: magnetar. A neutron star whose defining characteristic is not its spin, not its temperature, not even its density, but its magnetic field. A field so intense that it dominates every other physical process happening on or near the star. A field measured not in the trillions of Gauss like an ordinary pulsar, but in the quadrillions, 10 to the 14th Gauss at minimum, 10 to the 15th Gauss in the most extreme cases. To put that in perspective, the Earth's magnetic field, the one that makes compasses point north and protects us from solar wind, measures about half a Gauss. A strong refrigerator magnet is around 100 Gauss. The most powerful sustained magnetic field ever created in a laboratory on Earth, generated by the National High Magnetic Field Laboratory in Florida, tops out at around 45 Tesla, which converts to about 450,000 Gauss. A magnetar's field is roughly 10 billion times stronger than that. It is not an exaggeration to say that a magnetar's magnetic field is the strongest stable magnetic field the universe is capable of producing without collapsing into something even stranger. Duncan and Thompson's central argument was that neutron stars born under the right conditions could generate these fields naturally, not through some exotic process requiring new physics, but through a mechanism already known to operate in other astrophysical contexts. They called it a magneto-rotational dynamo, and the idea is both elegant and terrifying in its implications. Here's how it works. When a massive star collapses, the core doesn't just shrink, it spins up. This is conservation of angular momentum in action, the same principle that makes an ice skater spin faster when they pull their arms in. The collapsing core, already rotating slowly as part of the original star, suddenly finds itself compressed into a sphere 20 kilometers wide. That rotation accelerates dramatically. If the progenitor star was rotating even moderately fast before collapse, the newborn neutron star can end up spinning with a period of just a few milliseconds, 1,000 rotations per second. For the first few seconds after the bounce, the neutron star is not yet solid. It's a churning, convective fluid of neutrons, protons and electrons, all at temperatures exceeding 100 billion degrees. In that chaotic environment, with rapid rotation and violent convective currents, magnetic field lines can get twisted, stretched, and amplified. The process is similar to the dynamo that generates Earth's magnetic field, except it's running at 1,000,000 times the speed and 1,000,000,000 times the intensity. In the span of a few seconds, the magnetic field threading through the newborn neutron star can be amplified from a modest billion Gauss, typical of the progenitor star, to 10 to the 15th Gauss, a million-fold increase in field strength accomplished in the time it takes you to blink. The key requirement is rotation. Without fast rotation, the dynamo doesn't work. The convective motions alone aren't enough. You need the rapid spin to twist the field lines efficiently. That's why magnetars are rare. Most collapsing massive stars are not rotating fast enough at the moment of core collapse to trigger the dynamo. They produce ordinary neutron stars with magnetic fields in the trillions of Gauss, strong by any reasonable measure, but not magnetar strong. Only about 1 in 10 supernovae, maybe fewer, spins up a core fast enough to cross the threshold. The rest produce pulsars. Duncan and Thomson made a specific prediction. If their model was correct, newborn magnetars should start their lives spinning very rapidly, with periods around 1 millisecond, and then they should slow down much faster than ordinary pulsars. The reason is straightforward. A magnetar's enormous magnetic field acts like a brake. As the neutron star rotates, the magnetic field drags against the surrounding space, siphoning off rotational energy and converting it into radiation and magnetic energy. The stronger the field, the faster the slowdown. Within a few thousand years, a magnetar born spinning 1,000 times per second could slow to a rotation period of several seconds. By the time it reaches 10,000 years old, it might be spinning once every 10 seconds or slower, and its magnetic field, though still extraordinarily strong, would have decayed enough that the star stops producing dramatic bursts. It fades into the background, becoming just another neutron star in the census, its violent youth buried in the past. This prediction was testable. If you could measure the spin period of an SGR or an AXP and watch how fast it was slowing down, you could calculate the strength of its magnetic field. And if that field strength came out in the range of 10 to the 14th or 10 to the 15th Gauss, you'd have confirmation that the magnetar model was on the right track. The first confirmation came in 1998. Astronomers using the Rossi X-ray Timing Explorer, a NASA satellite designed to measure rapid variations in X-ray sources, observed an SGR designated 1806-20, the same object that had produced the first detected burst back in 1979. They measured its spin period at 7.5 seconds and, more importantly, they measured how fast that period was increasing. The star was slowing down at a rate consistent with a magnetic field of about 10 to the 15th Gauss. The numbers matched. The magnetar model had predicted exactly this kind of behavior, and here it was, written plainly in the data. Christopher Thompson, one of the model's architects, described the moment with characteristic understatement. We found that the only way of explaining the burst was with the idea of intense magnetism. It wasn't a guess, it wasn't a preference, it was the only explanation that closed the loop. Once you allowed for magnetic fields that strong, the anomalies disappeared. The slow rotation made sense. The X-ray luminosity made sense. The repeated bursts made sense. Everything clicked into place. The Magnetar hypothesis also offered a unifying framework for understanding both SGRs and AXPs. For years, the two classes of objects had been treated separately, as if they were unrelated phenomena that just happened to both involve neutron stars. The Magnetar model suggested they were the same thing at different stages of life. An SGR is a young, active magnetar, still producing violent bursts as its crust cracks under magnetic stress. An AXP is an older magnetar, past its burst-heavy phase, but still radiating X-rays powered by the slow decay of its magnetic field. The line between the two is blurry, not sharp, because the transition happens gradually over thousands of years. Some objects sit right on the boundary, showing characteristics of both classes. This was a profound shift. It meant the zoo of mysterious neutron stars wasn't actually a zoo, it was a timeline. You start with a newborn magnetar, spinning fast, bursting frequently. Over a few thousand years, the spin slows, the bursts become less frequent, and the object transitions from SGR to AXP. Over tens of thousands of years, the magnetic field decays further, the X-ray emission drops, and the magnetar fades into the general population of neutron stars, indistinguishable from its less magnetic cousins, except through careful measurement. But there was a problem, a big one. Duncan and Thompson's dynamo model explained how you could amplify a magnetic field during the chaotic first few seconds after a neutron star's birth. It didn't explain where the initial field came from. Every star has a magnetic field generated by currents of ionized gas moving through its interior. When the core collapses, that field gets compressed and amplified by a factor of about 1 billion just from the shrinkage alone. That gives you a starting field of roughly 1 trillion Gauss, which is already strong but nowhere near magnetar strength. To get from there to 10 to the 15th Gauss, you need the dynamo. Fine, but what if the progenitor star had a much stronger magnetic field to begin with? This is where the fossil field hypothesis comes in. Some massive stars, particularly those that form in binary systems or from turbulent gas clouds, are born with unusually strong magnetic fields. These fields can reach a few thousand Gauss, much stronger than the Sun's field. When such a star collapses, the compression alone can amplify that field to magnetar levels without requiring a dynamo at all. The strong magnetic field is simply inherited from the parent star, preserved and concentrated during the collapse. It's a fossil, a relic of the star's earlier life, frozen into the neutron star's structure. The fossil field theory and the dynamo theory are not mutually exclusive. Both mechanisms could operate. Some magnetars might be born from the dynamo process, others from fossil fields, and some from a combination of both. The debate over which mechanism dominates has been running for more than 20 years now, and it remains unresolved. The challenge is that you can't directly observe what's happening in the first few seconds after a neutron star forms. The supernova explosion is too bright, too chaotic, and too brief. By the time the debris clears enough to see the neutron star underneath, whatever process created its magnetic field has already finished. What astronomers can do is look for clues in the progenitor stars. If the fossil field theory is correct, magnetars should preferentially come from massive stars that were rapidly rotating or in close binary systems, because those are the stars most likely to have strong magnetic fields. If the dynamo theory is correct, magnetars should come from any massive star that happened to be rotating fast enough at the moment of collapse, regardless of its magnetic field before that point. The observational evidence leans slightly toward the dynamo model, but the fossil field explanation hasn't been ruled out. One surprising fact worth sitting with is that magnetars were predicted before they were confirmed. The name, the model, and the theoretical framework all existed years before astronomers had strong observational evidence that such objects were real. Duncan and Thompson published their Magnetar paper in 1992. The first solid confirmation that SGRs had magnetic fields in the Magnetar range didn't come until 1998. For 6 years, magnetars were a theoretical idea, floating in the literature, waiting for reality to catch up. That's rare in astrophysics. Usually, the observations come first and the theory scrambles to explain them. In this case, the theory arrived early and sat patiently while the telescopes did their work. By the early 2000s, the Magnetar hypothesis had moved from fringe idea to mainstream acceptance. More SGRs and AXPs were discovered. Their spin periods and slowdown rates were measured. Every single one of them pointed to magnetic fields in the 10 to the 14th to 10 to the 15th Gauss range. The model had passed every test thrown at it, and yet, even with the framework largely settled, the details remained murky. How exactly does the dynamo amplify the field? What percentage of massive stars produce magnetars? How long does a magnetar stay active? Can a magnetar ever reactivate after it has quieted down? These questions are still open. The magnetar model is accepted because it works, because it explains the observations better than any alternative, but it is not complete. The physics of neutron star interiors operates at energy densities and pressures that we cannot replicate on Earth. The equations governing magnetic field evolution in a convective, rotating nuclear density fluid are hideously complicated. Simulations help, but they rely on approximations. The ground truth is out there in space, locked inside objects we can only observe from thousands of light years away. What makes the Magnetar hypothesis so compelling is not just that it solved the mystery of SGRs and AXPs. It's that it opened a window into a regime of physics we had never accessed before. Magnetic fields at 10 to the 15th Gauss do things that no laboratory experiment can reproduce. They warp space-time. They twist the quantum vacuum. They make atoms elongate into cigar shapes. They bend light, and they store enough energy to power bursts of radiation visible across the galaxy. That energy doesn't just sit there. It leaks out, slowly at first, then sometimes all at once. The neutron star's crust, stressed by the twisting magnetic field, can crack like ice on a frozen lake. When it does, the sudden rearrangement of the magnetic field lines releases a flood of energy. In a fraction of a second, a magnetar can unleash more energy than our sun will produce in 200,000 years. That is not a metaphor. That is the measured output of magnetar flares detected by satellites in Earth orbit. The mechanism behind those flares is still not fully understood. The basic picture is that magnetic energy builds up over years or decades as the field slowly twists and deforms. Eventually, the stress exceeds what the crust can handle. The crust fractures. The field lines, suddenly free to move, snap back toward a lower energy configuration, like a rubber band that's been stretched too far. The energy released during that snap heats the surface of the magnetar to billions of degrees and accelerates particles to nearly the speed of light. Those particles collide with the magnetar's thin atmosphere, producing gamma rays and X-rays that spray outward in all directions. If Earth happens to be in the line of fire, our satellites pick up the signal. One of the most famous magnetar flares was detected on December 27, 2004. It came from SGR 1806-20, the same object that had been producing small bursts for decades. This time, the burst wasn't small. It was the most intense gamma-ray event ever recorded from a source outside our solar system. The initial spike lasted about 1/10 of a second and was so bright that it saturated every gamma-ray detector in orbit. For a brief moment, the Magnetar outshone every other X-ray and gamma-ray source in the sky combined. The afterglow of the flare lasted for months. The energy released in that single burst was estimated at about 10 to the 46 ergs, which is roughly equivalent to the total energy output of our Sun over 150,000 years. One burst, 1/10 of a second, 150,000 years of sunlight. And the object producing it was 12 miles wide. The Magnetar hypothesis didn't just explain what SGRs and AXPs were. It explained what they were capable of, and it forced physicists to confront a reality they had not anticipated. Magnetic fields, usually thought of as secondary players in the cosmic drama, subordinate to gravity and nuclear forces, could under the right circumstances become the dominant force shaping a star's behavior. Magnetars are not stars held together by nuclear fusion or by the balance between pressure and gravity. They are stars held together and torn apart by magnetism. The magnetic field isn't a detail, it's the story. That realization changed how astronomers thought about neutron stars in general. It meant there were entire classes of behavior, entire phenomena that could only happen in the presence of magnetic fields orders of magnitude stronger than anything we had previously considered. And if magnetars existed, if the universe could build magnetic fields that strong, what else was lurking out there in the graveyard, waiting to be found? The answer, as it turned out, was even stranger than the question. We need to talk about what a magnetic field actually does at the scale magnetars operate, not in the abstract, not as a number on a graph, but as a physical force reshaping reality in ways that should make you deeply uncomfortable. Because the magnetic field around a magnetar is not just strong, it is so strong that it crosses a threshold most people don't know exists. A line past which the rules governing matter, light, and even empty space itself stop working the way they're supposed to. Start with the comparison everyone uses, because it's the only way to anchor the scale to something human brains can process. Earth has a magnetic field. It's weak, roughly half a Gauss at the surface, but it's enough to deflect charged particles from the solar wind and keep our atmosphere from getting stripped away. It's enough to make a compass needle swing north. It's the reason we have auroras, and the reason our electronics don't get fried every time the sun burps. It's subtle, protective, and entirely invisible unless you're holding a piece of magnetized metal. A magnetar's magnetic field is about 1,000 trillion times stronger than Earth's. That number is not rounding. It's not exaggeration. A typical magnetar has a surface magnetic field of around 10 to the 15th Gauss. Earth's field is about 0.5 Gauss. Divide one by the other and you get a ratio of 2 times 10 to the 15th, 2 quadrillion. 1,000 trillion is shorthand, and it undersells the reality slightly, but the point stands. We are talking about a difference so vast that the comparison itself barely functions. Here's another way to frame it. The strongest sustained magnetic field ever created in a laboratory on Earth, generated at the National High Magnetic Field Laboratory in Florida using superconducting magnets and an enormous amount of carefully managed electrical current, tops out at about 45 Tesla. That converts to roughly 450,000 Gauss. It took decades of engineering, millions of dollars in funding, and a facility the size of a building to produce that field, and it represents the absolute pinnacle of what human technology can achieve in a controlled environment. A magnetar's field is 10 billion times stronger than that. 10 billion times stronger than the most powerful magnet humanity has ever built. And it exists naturally, threaded through a ball of neutrons 12 miles wide, sitting in the vacuum of space, requiring no power supply, no cooling system, no team of engineers. It's just there. It has always been there, and it will stay there for thousands of years. At that field strength, physics changes, not metaphorically, literally. The equations that describe how particles and light behave in ordinary magnetic fields stop being accurate. You have to bring in quantum electrodynamics, the branch of physics that governs how light and matter interact at the smallest scales, and even then, you're working at the edge of what the theory has been tested against. Because no laboratory on Earth has ever come close to creating the conditions that exist on a Magnetar's surface. We can write down the equations, we can run simulations, we can make predictions, but we cannot test them directly. The only laboratory capable of running these experiments is the universe itself, and it doesn't publish its method section. Quantum electrodynamics, usually abbreviated QED, is one of the most successful theories in all of physics. It describes how photons, the particles of light, interact with electrons and other charged particles. It has been tested to absurd levels of precision. Some QED predictions match experimental results to better than 1 part in a billion. It is as close to a proven framework as physics gets. But like every theory, it has a domain of validity. There are regimes where QED works perfectly and regimes where it starts to show cracks. One of those regimes involves very strong magnetic fields. There is a specific number in QED called the critical field strength. Physicists usually denote it as B sub Q, and its value is about 4.4 times 10 to the 13th Gauss. This is not an arbitrary threshold. It comes directly from the fundamental constants of nature. The critical field is the point at which the energy stored in the magnetic field over a distant scale set by the electron's quantum properties becomes comparable to the rest mass energy of an electron. In simpler terms, it's the point where the magnetic field itself becomes strong enough to do things that normally require particle accelerators. Below that field strength, magnetism behaves more or less the way you learnt it behaves in school. Above that field strength, the vacuum of space stops being empty. A magnetar's surface field sits right around 10 to the 15th Gauss. That's about 20 times the QED critical field. Some magnetars, the most extreme ones, may have fields closer to 10 times the critical threshold. Either way, they are firmly in the regime where quantum electrodynamics predicts genuinely weird effects. Effects that have never been observed in a laboratory. Effects that, until magnetars were confirmed to exist, were purely theoretical curiosities discussed in the back pages of textbooks. Now they are observable astrophysical phenomena. The universe built a QED laboratory in space, and we didn't even realize it until the 1990s. One of the most striking predictions of QED in strong magnetic fields is a phenomenon called vacuum birefringence. The word sounds technical, and it is, but the concept is straightforward enough. Birefringence means that a material has two different refractive indices depending on the polarization of the light passing through it. Certain crystals on Earth, like calcite, are birefringent. If you shine light through a calcite crystal, the light splits into two beams, each with a different polarization, and the two beams travel at slightly different speeds through the material. This is a well-understood effect. It's been known for centuries. It happens because the crystal's internal structure affects light differently, depending on how the light's electric field is oriented. What QED predicts is that a strong magnetic field does the same thing to empty space. Not to a crystal, not to a gas, not to any material substance, to the vacuum itself. In the presence of a magnetar-strength magnetic field, space becomes birefringent. Light traveling through that space will experience different refractive indices depending on whether its polarization is aligned parallel or perpendicular to the magnetic field. The two polarizations will travel at slightly different speeds. One will be delayed relative to the other. The vacuum, which we usually think of as nothing, begins to behave like something. The reason this happens has to do with virtual particles. Quantum field theory tells us that the vacuum is not truly empty. It's filled with fluctuations, pairs of particles and antiparticles that pop into existence for incredibly brief moments and then annihilate. Normally, these fluctuations have no observable effect because they happen so quickly and at such small scales that they average out to zero. But in a strong magnetic field, the vacuum fluctuations get polarized. Electron-positron pairs, the most common type of virtual particle pair, align themselves with the magnetic field. That alignment changes the way light propagates through the vacuum. The field effectively gives the vacuum an internal structure, and that structure is birefringent. This is not speculation. This is a direct, calculable prediction of QED. The equations are clear. The effect should happen. The challenge is detecting it. On Earth, even the strongest magnetic fields we can produce are far too weak to make vacuum birefringence measurable. The effect scales with the square of the magnetic field strength, so you need to be very close to the QED critical field before the effect becomes large enough to see. Magnetars are the only known objects in the universe that cross that threshold. If vacuum birefringence exists, and QED says it must, then magnetars are where we should see it. Astronomers have been searching for the signature of vacuum birefringence in magnetar light for more than 2 decades. The idea is simple. Light emitted from a magnetar's surface will be polarized as it passes through the intense magnetic field surrounding the star. If the vacuum is birefringent, the polarization will rotate as the light travels outward. By the time the light reaches Earth, the polarization angle will have shifted by an amount that depends on the strength and geometry of the magnetic field. Measure the polarization, compare it to what you'd expect without birefringence, and you can test whether QED is right. The problem is that polarization measurements in X-rays, which is where most magnetar emission happens, are extremely difficult. For years, the instruments simply weren't sensitive enough. Then, in late 2021, NASA launched the Imaging X-ray Polarimetry Explorer, usually called IXPE. It was the first space telescope specifically designed to measure X-ray polarization with high precision. Within months of going online, IXPE pointed at several magnetars and began collecting data. The early results, published through 2023 and 2024, showed exactly the kinds of polarization signatures that vacuum birefringence would produce. The light from magnetars was highly polarized, and the polarization angle changed in ways consistent with the light passing through a birefringent vacuum shaped by an ultra-strong magnetic field. The measurements weren't definitive proof. There are other effects related to the geometry of the magnetar's emission regions and the scattering of light in the thin atmosphere above the neutron star's surface that can also affect polarization. Disentangling those effects from vacuum birefringence requires careful modeling and more observations. But the data were encouraging. They pointed in the direction QED predicted. As of early 2025, astronomers are still working through the IXPE data, refining their models and planning follow-up observations. The consensus seems to be that vacuum birefringence is probably happening, but the confirmation is not yet ironclad. The effect is there, lurking in the data, but it's tangled up with a lot of other physics. That's how science works at the frontier. You don't get clean answers right away. You get hints, patterns, small pieces of evidence that slowly accumulate until the picture becomes clear. Magnetars are giving us that picture, one photon at a time. While light is being bent by the vacuum, matter itself is being crushed into shapes that shouldn't exist. Atoms, the building blocks of everything you can see and touch, are held together by electromagnetic forces. The nucleus sits at the center, positively charged, and the electrons orbit around it, negatively charged, held in place by the attraction between opposite charges. In weak magnetic fields, the atom's shape is more or less spherical. The electron cloud spreads out evenly in all directions. This is the configuration you learn about in chemistry class, the one that appears in every diagram of an atom you've ever seen. In a magnetar strength magnetic field, that configuration collapses. The magnetic field exerts an enormous force on the electrons, far stronger than the electric force holding the atom together. The electrons, being charged particles, feel the magnetic force and respond by confining themselves to motion along the field lines. The electron cloud, which was spherical, gets compressed perpendicular to the field and stretched parallel to it. The atom warps into a cigar shape, not a metaphorical cigar, a literal elongated ellipsoid, orders of magnitude longer in one direction than the other. The degree of deformation depends on the field strength and the type of atom. Hydrogen, the simplest atom, gets stretched the most. In a field of 10 to the 13th Gauss, just below the QED critical field, a hydrogen atom's electron cloud can be squeezed down to a cross-sectional radius hundreds of times smaller than its normal size, while stretching along the field direction by a similar factor. At 10 to the 15th Gauss, the deformation is even more extreme. The atom stops looking like an atom and starts looking like a needle. This has profound implications for the chemistry and the material properties of anything near a magnetar. Normal chemistry depends on atoms being able to bond with each other in predictable ways. Those bonds depend on the shape and size of the electron clouds. When the electron clouds are deformed by a factor of 100 or more, the bonds don't form the way they should. Molecules that are stable on Earth would be unstable near a magnetar. Materials that are solid under normal conditions would behave like liquids or gases. The entire concept of chemical structure, as we understand it, breaks down. The surface of a neutron star, magnetar or otherwise, is thought to be made of a solid crust composed mostly of iron nuclei arranged in a crystalline lattice. In a normal neutron star, that crust is already exotic. The density is so high that the nuclei are packed far more tightly than in any material on Earth, and the electrons move freely between them in a kind of metallic state. On a magnetar, the magnetic field adds another layer of strangeness. The electron gas becomes highly anisotropic, meaning its properties depend strongly on direction. Conductivity along the magnetic field lines is very different from conductivity perpendicular to them. Heat flows preferentially along the field. Mechanical stress builds up in directions perpendicular to the field. The crust is no longer a simple solid. It's a magnetically structured material with properties that change depending on which way you're looking, and that crust is under constant strain. The magnetic field threading through the neutron star is not static. It evolves over time, twisting and reconfiguring as the star spins and as currents flow through its interior. The energy stored in the magnetic field is enormous, and that energy has to go somewhere. Some of it leaks out as radiation. Some of it gets stored as stress in the crust, bending and twisting the solid iron lattice like a piece of metal being bent back and forth. Eventually, the stress exceeds what the crust can handle. The crust fractures. And when it does, the magnetic field lines that were held in place by the crust suddenly snap free. This process is called magnetic reconnection, and it's the leading explanation for magnetar bursts. Reconnection happens when magnetic field lines that are twisted or tangled suddenly break and rejoin in a lower energy configuration. The energy that was stored in the twisted field gets released almost instantaneously, heating the surrounding material to billions of degrees and accelerating particles to nearly the speed of light. On the Sun, magnetic reconnection is what powers solar flares. On a magnetar, it's what powers bursts that can be detected from halfway across the galaxy. The timescale for reconnection is shockingly fast. Theoretical estimates suggest that in a magnetar's magnetic field, reconnection can happen in about 1 millisecond, 1,000th of a second. That's faster than the blink of an eye. It's faster than a neuron fires. In that millisecond, the magnetic field reconfigures, and the energy equivalent to what our Sun will produce over thousands of years floods outward into space. But here's the puzzle. The observed bursts from magnetars don't last 1 millisecond. The giant flare detected from SGR 1806-20 in December 2004, the most intense gamma-ray event ever recorded from outside the solar system, had an initial spike that lasted about a quarter of a second. A quarter of a second is 250 milliseconds. That's more than 200 times longer than the reconnection timescale. So if the energy is released in 1 millisecond, why does the burst last for a quarter of a second? The answer is still being worked out, but the leading idea is that the burst we see is not the reconnection itself, it's the aftermath. The reconnection happens deep in the magnetar's magnetosphere, the region of twisted magnetic fields surrounding the star. The energy released heats a thin layer of the neutron star's surface to extreme temperatures, and that hot surface radiates X-rays and gamma rays for as long as it stays hot. The surface doesn't cool instantly. It takes time for the energy to spread out and for the temperature to drop. That cooling time, not the reconnection time, sets the duration of the burst we observe. There's also the possibility that multiple reconnection events happen in quick succession, each one feeding energy into the burst over a span of several hundred milliseconds. The magnetic field in a magnetar's magnetosphere is incredibly complex, tangled in 3 dimensions like a ball of yarn that's been dropped and kicked around. One reconnection event could trigger others nearby, creating a cascade. The result would be a burst that lasts much longer than any single reconnection event, even though each individual snap happens in a millisecond. Magnetic reconnection is not unique to magnetars. It happens in Earth's magnetosphere during geomagnetic storms. It happens in the Sun's corona, powering solar flares and coronal mass ejections. It happens in the accretion disks around black holes. Anywhere you have a magnetic field that gets twisted and stressed, you can get reconnection. What makes magnetars special is the scale. The magnetic field is so strong and the energy density so high that reconnection releases more energy in a fraction of a second than the Sun produces in a century. It's the same physics, just turned up to a level that makes every other example look tame. And it's not just the field strength, it's the field geometry. Magnetar magnetic fields are not simple dipoles, the kind you get from a bar magnet with a north pole and a south pole. They're twisted, tangled, multipolar structures with field lines looping and knotting in 3 dimensions. Some of that complexity comes from the dynamo process that generated the field in the first place. Some of it comes from the star's rotation, which winds the field lines up like a spring. Some of it comes from motion in the neutron star's interior, where currents of charged particles push and pull on the field. The result is a magnetic field configuration that's inherently unstable. It wants to relax into a simpler, lower energy state. But to do that, it has to break and reconnect, and when it does, we see a burst. Most of the time, magnetars are quiet. They sit in space, spinning slowly, radiating a steady glow of X-rays powered by the slow decay of their magnetic fields. Then, without warning, the crust cracks, the field reconnects, and for a brief moment, the magnetar becomes the brightest object in the X-ray and gamma-ray sky. The burst fades, the magnetar goes quiet again. Months or years pass, then it happens again. We don't know what triggers the cracks. We don't know why some magnetars burst frequently while others seem to go decades without producing a single major flare. We don't know if there's a pattern or if it's random. What we do know is that the bursts are tied to the magnetic field. The energy comes from the field. The timescale is set by reconnection. The brightness depends on how much energy was stored and how quickly it got released. Every piece of the puzzle points back to the same answer. The magnetic field is not just strong. It is the dominant force shaping the magnetar's behavior, and it is capable of unleashing violence on a scale that defies comfortable comprehension. There's one more effect worth mentioning before we move on, and it's subtle but crucial. A magnetic field as strong as a magnetar's doesn't just affect matter and light. It affects space-time itself. General relativity tells us that energy warps space-time, creating what we experience as gravity. Normally, when we talk about warping space-time, we're talking about mass. A star, a planet, a black hole, all of them curve space-time because they contain mass, and mass is a form of energy. But magnetic fields also contain energy. And if the field is strong enough, that energy can warp space-time in measurable ways. A magnetar's magnetic field contains roughly the same amount of energy as the sun will radiate over 100,000 years. That energy is not distributed evenly through space. It's concentrated in a small region around the neutron star, threaded through the star's interior and wound tightly in the magnetosphere. The energy density is high enough that it contributes to the star's overall gravitational field. Not by a huge amount, but by enough that in principle you could detect it if you had precise enough measurements. The magnetic field makes the magnetar slightly heavier than a non-magnetized neutron star of the same mass. It also makes spacetime around the magnetar slightly more curved. This is not just theoretical. It's been calculated. The effect is small, but it's real, and it shows up in the equations. The presence of the magnetic field shifts the neutron star's radius slightly, changes the way light bends as it passes nearby, and alters the star's moment of inertia in ways that affect how fast it spins. None of these effects are large enough to dominate the star's behavior. The mass of the neutron star is still the main thing shaping spacetime in its vicinity, but the magnetic field contributes. It's a player in the game, not just a spectator. What all of this adds up to is a picture of an object where the normal hierarchy of forces has been inverted. In most of the universe, gravity is the dominant force at large scales, and electromagnetism is dominant at small scales. On a magnetar, magnetism competes with gravity even at the scale of the entire star. The magnetic pressure, the outward push exerted by the field, is comparable to the gravitational pressure trying to crush the star inward. The two forces are locked in a tense balance, and that balance is unstable. The field is constantly evolving, the crust is constantly stressed, and every so often something gives. When it does, the result is not subtle. It's a burst of gamma rays and X-rays bright enough to light up detectors on the other side of the galaxy. A burst powered not by nuclear reactions, not by the infall of matter, but by the snapping and reconfiguring of magnetic field lines in a vacuum that has stopped being empty. And the burst, as violent as it is only a symptom, a whisper from the surface of an object whose very existence pushes physics into a regime we have never fully explored. On the morning of December 27, 2004, at roughly 21 hours 30 minutes and 26 seconds Universal Time, every gamma-ray detector in orbit around Earth went blind. Not because they malfunctioned, because something in space hit them with so much energy that their sensors saturated instantly, overwhelmed by a flood of high-energy photons arriving faster than the instruments could count. For a fraction of a second, the detectors could do nothing but register that they were being blasted by something unprecedented. Then the initial spike faded, and the instruments came back online, still recording a decaying tale of gamma rays and X-rays that would continue for minutes. By the time the event was over, astronomers had recorded the brightest explosion of high-energy radiation ever observed from beyond our solar system. Not the brightest supernova, not the brightest gamma-ray burst from a collapsing star. The brightest burst, period, in the entire history of gamma-ray astronomy. The source was a magnetar, specifically SGR 1806-20, an object that had been known since 1979 when it first showed up as a soft gamma repeater. It sits on the far side of the Milky Way, roughly 50,000 light-years from Earth, buried in a region of the galaxy dense with gas and dust. Invisible light, you cannot see it. The intervening material blocks optical wavelengths completely. The only reason we know it exists at all is because gamma rays and X-rays punch through the dust without much trouble, and magnetars produce plenty of both. SGR 1806-20 had been quiet for years before December 2004. It had produced small bursts in the past, the kind that last a few tenths of a second and release modest amounts of energy by magnetar standards. Nothing unusual. Nothing that suggested it was about to do anything particularly dramatic. Then on December 27th, it woke up. The flare lasted about 1/10 of a second at its peak, 0.1 seconds, the time it takes for a hummingbird to complete a single wing beat. In that window, the magnetar released approximately 2 × 10⁻46 ergs of energy. That number does not mean much in isolation, so let's translate it. The Sun, our Sun, the star that powers every living thing on this planet, radiates about 4 × 10⁻33 ergs per second. It has been doing that for roughly 4.5 billion years and will continue doing it for another 5 billion. Over the course of a single year, the Sun emits about 1.2 × 10⁻41 ergs. Divide the flare energy by the Sun's annual output, and you get a number in the neighborhood of 150,000 to 200,000 years, depending on exactly how you account for the flare's duration and geometry. Different analyses land on slightly different figures. Some sources say 100,000 years, some say 250,000. The exact number doesn't matter. The point is that a single burst from a magnetar, lasting a fraction of a second, carried more energy than our Sun will radiate over a span of time longer than human civilization has existed. Let that sit. Humans have been writing things down for maybe 5,000 years. We have had cities for maybe 10,000. Anatomically modern humans have existed for perhaps 300,000 years. The flare from SGR 1806-20 in December 2004 packed more energy into 1/10 of a second than the Sun will produce over a stretch of time that dwarfs all of recorded history, all of agriculture, all of written language, and a significant fraction of our existence as a species. One object, one burst, 1/10 of a second. The initial spike was so intense that it did not just saturate the detectors on dedicated gamma-ray satellites. It affected Earth's ionosphere. The ionosphere is the upper layer of our atmosphere, roughly 50 to 600 kilometers above the surface, where ultraviolet light from the sun strips electrons off atoms and creates a layer of charged particles. That ionized layer reflects certain radio frequencies, which is why you can sometimes pick up AM radio stations from hundreds of miles away at night when the ionosphere is more stable. The ionosphere is shaped primarily by solar radiation. The sun is 93 million miles away, but it is bright enough and energetic enough that its ultraviolet and X-ray output constantly reshapes the ionosphere's density and structure. The Magnetar flare, arriving from 50,000 light-years away, was strong enough to compress the ionosphere on the day side of Earth, not by a lot, not enough to cause any lasting damage, but enough that instruments monitoring the ionosphere detected the change in real time. A burst of gamma rays and X-rays from halfway across the galaxy had reached through space, passed through our planet's magnetic field, and briefly altered the structure of our upper atmosphere. That is how bright it was. That is how much energy was involved. Berkeley's Space Sciences Laboratory, which operates instruments on several gamma-ray satellites, put out a press release shortly after the event, calling it the brightest explosion ever recorded in terms of high-energy X-rays and gamma rays. The wording is careful. Supernovae are brighter in total luminosity when you include all wavelengths. Gamma-ray bursts from collapsing massive stars can be more luminous if you integrate over their full duration. But for sheer peak brightness in the gamma-ray and X-ray bands, nothing humanity has ever detected comes close to the December 2004 flare from SGR 1806-20. And the kicker is that if the Magnetar had been closer, say within a few thousand light-years instead of 50,000, the burst would have been catastrophic for Earth. Not in the sense of blowing up the planet. Gamma rays do not work that way. But in the sense of stripping a significant portion of the ozone layer, irradiating the surface, and potentially triggering a mass extinction event, we got lucky. The Magnetar was far enough away that the inverse square law diluted the burst to merely record breaking instead of apocalyptic. So what actually happened? What causes a Magnetar to release that much energy that quickly? The mechanism is magnetic. We have established that magnetars have magnetic fields in the range of 10 to the 15th Gauss, threaded through their interiors and extending outward into a tangled magnetosphere. That field is not stable. It evolves over time. The neutron star is spinning, though slowly by pulsar standards. Currents of charged particles flow through the star's interior, driven by the decay of the magnetic field and by the residual heat left over from the star's formation. Those currents push and pull on the magnetic field lines, twisting them, winding them up like a spring. The energy that goes into twisting the field does not disappear. It gets stored as magnetic energy, locked into the geometry of the field itself. The neutron star's crust, a solid lattice of iron nuclei and free electrons, is caught in the middle. The magnetic field threads through the crust, and as the field twists, it exerts stress on the solid material. The crust is strong. Neutron star matter at nuclear density can withstand pressures and stresses that would vaporize any material on Earth, but it is not infinitely strong. There is a limit to how much stress it can handle, and when the magnetic field twists far enough, the stress exceeds that limit. The crust fractures. Astronomers call this a starquake. Starquakes are not earthquakes. They are not slow, grinding movements of tectonic plates. They are catastrophic failures of a crystalline lattice under enormous magnetic stress. When the crust cracks, two things happen almost simultaneously. First, the shape of the neutron star changes slightly. The crack allows a small region of the crust to shift position, and because the star is spinning, that shift changes its moment of inertia. Conservation of angular momentum forces the star to adjust its rotation rate. This is measurable. After a starquake, a magnetar's spin period changes by a tiny amount, usually speeding up slightly. The change is tiny, on the order of microseconds, but it is detectable from Earth with precise timing instruments. Second, and more dramatically, the magnetic field lines that were held in place by the now fractured crust suddenly snap free. They are no longer locked into the solid lattice. They are free to move, and they do. The twisted, stressed magnetic field reconfigures itself, seeking a lower energy state. The process is called magnetic reconnection, and it is the same mechanism that powers solar flares on the Sun. But on the Sun, magnetic reconnection releases energies on the order of 10 to the 32 ergs. On a magnetar, with a field a trillion times stronger, reconnection releases energies in the 10 to the 46 erg range, a million trillion times more energy than a solar flare. The reconnection happens fast. Theoretical models suggest it occurs on a timescale of about 1 millisecond, 1,000th of a second. In that millisecond, the magnetic field snaps into a new configuration, and the energy that was stored in the twisted field lines floods outward. Some of that energy goes into heating the surface of the neutron star. Some goes into accelerating particles to nearly the speed of light, and some goes into creating a fireball. The fireball is a key part of the story. When magnetic reconnection dumps that much energy into a small region of space, the immediate result is not a clean burst of gamma rays flying outward. What happens instead is that the energy creates pairs of particles and antiparticles, primarily electrons and positrons, out of the vacuum. This is quantum electrodynamics in action. If you have enough energy in a small enough volume, that energy can spontaneously convert into matter, specifically into particle-antiparticle pairs. The pairs are created in enormous numbers, trillions upon trillions of them, all crowded into a region just above the neutron star's surface. This is called a pair plasma, and it is opaque. Photons cannot escape it easily because they keep scattering off the electrons and positrons. The plasma traps the energy, at least initially. The region becomes a fireball, a hot, dense, trapped ball of light and matter sitting just above the magnetar's surface. The fireball is at a temperature of billions of degrees, hot enough that it radiates primarily in gamma rays and X-rays, and it expands. The pressure inside the fireball pushes it outward at close to the speed of light. As it expands, it cools, and as it cools, it becomes less opaque. Eventually, after a few tenths of a second, the fireball has expanded and cooled enough that the gamma rays can finally escape. That is what we see as the initial spike. So the burst we detect is not the reconnection event itself. The reconnection happens in a millisecond, deep in the magnetosphere. The burst we see is the fireball expanding and cooling, and finally releasing its trapped radiation into space. The initial spike, that fraction of a second where every detector went blind, corresponds to the moment when the fireball became transparent. Before that moment, the energy was there, trapped in the plasma, invisible to us. After that moment, it floods outward. The December 2004 flare from SGR 1806-20 did not end with the initial spike. That was just the beginning. After the spike faded, the detectors continued to record a decaying tail of gamma rays and X-rays that lasted for several minutes, and embedded in that tail was something strange. The emission was not smooth, it oscillated. The brightness went up and down in a regular pattern, with a period of about 5 seconds. That period matches the Magnetar's rotation period. The star was spinning once every 5 seconds, and as it spun, the hot spot on its surface, the region heated by the flare, rotated in and out of view. Each time the hot spot faced Earth, the brightness increased. Each time it rotated away, the brightness dropped. The oscillations lasted for hundreds of seconds, gradually fading as the surface cooled. But there was more structure in the light curve. In the first 600 milliseconds after the initial spike, the emission showed repeated bursts of energy, suggesting that the magnetic field was not reconfiguring all at once. It was snapping and reconnecting in multiple stages, each one injecting more energy into the fireball. The detailed shape of the light curve, the timing of the oscillations, and the rate at which the tail decayed all carry information about the Magnetar's structure, its magnetic field geometry, and the physics of the reconnection process. Astronomers have spent years analyzing that data, building models, trying to extract every piece of information the flare has to offer. One of the most important conclusions from those analyses is that the flare required more energy than could be stored in the Magnetar's external magnetic field alone. The energy released, roughly 2 × 10⁴ ergs, is on the same order as the total magnetic energy in the magnetosphere, but it is uncomfortably close to the limit. If the external field is all you have, you are tapping nearly all of it in a single event. That seems unlikely. The more plausible explanation is that the Magnetar has a much stronger magnetic field buried deep in its interior, a field that threads through the core and is not directly observable from the outside. That internal field could hold 10⁴ ergs or more, far exceeding the energy in the external field. When a starquake cracks the crust and triggers reconnection, it taps into that reservoir. The external field, the part we can measure by observing the Magnetar's spin-down rate and its surface emission, is just the tip of the iceberg. That has implications. It means Magnetars might be hiding even stronger fields than we thought. The 10⁻⁵ Gauss we measure at the surface might be understating the true strength of the field deeper inside. And if that is true, then the energy available for flares could be even larger than the December 2004 event. That flare, as bright as it was, might not represent the upper limit. There could be Magnetars capable of producing even more energetic bursts, and we just have not seen one yet. The December 2004 flare was not the first giant flare ever detected from a Magnetar. There had been 2 others, one in 1979 from a Magnetar in the Large Magellanic Cloud, and one in 1998 from a Magnetar in our own galaxy. Both were less energetic than the 2004 event, but both followed the same pattern. An initial spike lasting a fraction of a second, followed by a pulsating tail lasting minutes. The 2004 event was the brightest and the best observed, but it fit into a broader picture. Giant flares are rare. Most Magnetars never produce one during the time we have been watching them, but when they do happen, they are unmistakable. The rarity makes sense when you consider the energy budget. A giant flare releases a significant fraction of the Magnetar's stored magnetic energy. Once that energy is gone, it takes time to rebuild. The magnetic field has to twist up again, the crust has to accumulate stress again, and that process takes years or decades. Some Magnetars might go their entire active lifetimes without producing a giant flare. Others might produce one and then go quiet for centuries. We do not know how often these events happen on average, because we have only been watching Magnetars for a few decades, and the galaxy contains only a few dozen known magnetars. The sample size is small, the timescales are long. We are catching glimpses of a process that operates on its own schedule, indifferent to whether we happen to be looking. What we can say with confidence is that magnetar flares are detectable across enormous distances. The December 2004 flare came from 50,000 light-years away and still saturated detectors in Earth orbit. If the same flare happened in a nearby galaxy, say the Andromeda Galaxy, about 5 million light-years from Earth, we would still detect it. It would be fainter, yes, but not by much. The sensitivity of modern gamma-ray telescopes is good enough that a giant magnetar flare could be seen across a significant fraction of the local group of galaxies. And if the flare happened in our own galaxy, but closer to Earth, say within a few thousand light-years, the burst would be brighter than the full moon in gamma rays. That has led some researchers to propose that magnetar flares might explain certain transient gamma-ray sources that have been detected over the years but were never conclusively identified. There are events in the astronomical record, brief bursts of gamma rays that do not fit the profile of a supernova or a gamma-ray burst from a collapsing star, that could plausibly be distant magnetar flares. We will never know for sure in most cases because the events were not followed up in enough detail, but the possibility is there. Magnetars might be producing bright flares all the time, scattered across the universe, and we are just now starting to recognize them for what they are. The detectability of magnetar flares also raises a more uncomfortable question. If a magnetar flare happened close enough to Earth, what would it do? We have already established that the December 2004 event from 50,000 light-years away was strong enough to affect our ionosphere. That was a purely electromagnetic effect. The gamma rays and X-rays hit the upper atmosphere, ionized some additional atoms, and compressed the ionosphere slightly. No lasting damage, but scale that up. Bring the magnetar closer. If a giant flare like the December 2004 event happened within 10,000 light-years of Earth, the burst would be 25 times brighter because the intensity falls off with the square of the distance. At that brightness, the gamma rays and X-rays would deposit enough energy into the atmosphere to cause serious chemical changes. Ozone molecules, which protect the surface from ultraviolet radiation, would be broken apart. Nitrogen oxides would form in large quantities, further depleting the ozone layer. The result would be a temporary but significant thinning of the ozone layer, lasting months or years, during which time the surface of the Earth would be exposed to higher levels of solar ultraviolet radiation. Bring the magnetar even closer, within a few thousand light-years, and the effects get worse. The gamma rays would ionize the atmosphere more deeply, creating nitrogen oxides at lower altitudes. The ozone depletion would be more severe. Surface life would be directly affected. Plants would suffer. Marine ecosystems, particularly plankton, would be hit hard because many species are sensitive to ultraviolet radiation. And anything on the surface that happened to be facing the magnetar at the moment of the burst would receive a direct dose of gamma rays, not enough to kill a human instantly, but enough to increase cancer rates, damage DNA, and cause widespread biological harm. At a distance of 1,000 light-years or closer, a giant magnetar flare would be a mass extinction event. The ozone layer would be stripped away almost entirely. The surface would be bathed in ultraviolet light and gamma rays. Anything that could not hide underground or underwater would die within months. The fossil record contains several unexplained extinction events, periods where a significant fraction of species disappeared relatively quickly without an obvious cause, like an asteroid impact or massive volcanism. Some researchers have speculated that nearby gamma-ray bursts or magnetar flares could be responsible. There is no direct evidence for this, but the timescales and the severity of the damage match. A magnetar flare does not leave a crater. It does not leave layers of iridium in the geological record. It just irradiates the surface and moves on. If it happened in the past, we would have no way to prove it now. Fortunately, there are no known magnetars within 1,000 light-years of Earth. The nearest confirmed magnetar is at least a few thousand light-years away, far enough that even a giant flare would be more spectacle than threat. We can watch these events without worrying that they will hurt us. We are outside the danger zone. But the fact that the danger zone exists, that there is a distance inside which a magnetar flare becomes an existential threat to life on Earth, is worth keeping in the back of your mind. The universe is capable of producing events that could sterilize a planet from across interstellar distances. We live in a neighborhood where, for now, we are safe. That is luck, not law. The December 2004 flare was a watershed moment in magnetar research. It was the first giant flare observed with modern instruments, the first one where astronomers could measure the light curve in fine detail, track the oscillations, and build detailed models of what was happening. The data from that event have been analyzed and reanalyzed for more than 20 years now, and they continue to yield insights. Every time someone builds a new model of magnetic reconnection or runs a more sophisticated simulation of pair plasma fireballs, they go back to the December 2004 flare to see if the model matches the observations. It has become the benchmark, the standard against which all other magnetar flare theories are tested, and it raised the stakes. Before December 2004, magnetar flares were interesting, yes, but they were also abstract. Astronomers talked about magnetic energy and starquakes and field line reconnection, and it all sounded impressive, but it was hard to grasp the scale. The December 2004 flare made the scale visceral, 1/10 of a second, 100,000 years of sunlight, bright enough to affect Earth from halfway across the galaxy. Those are not numbers you forget. They are not numbers you can comfortably ignore. They force you to confront the reality that there are objects in the universe, not hypothetical, not theoretical, but real, observable, measurable objects that operate at energy scales we have no business comprehending. And here is the part that should keep you up at night. The December 2004 flare was not even the most energetic event a magnetar is theoretically capable of producing. It tapped a significant fraction of the magnetar's magnetic energy, yes, but not all of it. There is more in the tank. If a magnetar were to undergo a complete magnetic field reconfiguration, releasing all of its stored magnetic energy at once, the resulting burst could be 10 times brighter, 100 times brighter. We do not know if that can happen. We do not know if the physics allows for a total release, or if there are mechanisms that prevent it, spreading the energy out over multiple smaller flares instead. But the possibility is there. And if it happens, if a magnetar somewhere in the universe undergoes a catastrophic magnetic collapse and releases 10 to the 47 ergs in a single burst, we will see it, and we will have to explain it. And we will have to accept that the universe has once again demonstrated that our sense of scale is laughably inadequate. The flare was a whisper, a brief, blinding whisper from the edge of the cosmic graveyard, reminding us that the monsters we have been discussing are not sleeping. They are awake, they are violent, and they are capable of producing events so energetic that they challenge every comfortable assumption we have ever made about what dead stars are supposed to do. Black holes have held the title of scariest object in the universe for as long as most people have known what a black hole is. The name alone does most of the work. A hole in space. A region where gravity is so strong that nothing, not matter, not light, not information itself, can escape once it crosses the boundary. The event horizon is a one-way door. Step through it, and the universe behind you ceases to be a place you can ever return to. Your future becomes a singular point at the center where all paths lead inward and time itself runs out. It is the ultimate trap, permanent, absolute, inescapable. And for decades, that narrative has dominated popular imagination and scientific discourse alike. Black holes are the monsters. They are the objects that break the rules, that devour stars, that sit at the centers of galaxies growing fat on the accumulated mass of millions of suns. They warp space-time so severely that the math describing them contains singularities, points where the equations blow up and stop making sense. They are the places where physics goes to die, or at least to hide behind an impenetrable curtain. We cannot see what happens inside the event horizon. We can only infer, speculate, and build theories that may never be testable. Black holes are terrifying because they are unknowable. They are the universe's way of saying, beyond this point, the answers stop. And yet, for all their conceptual horror, black holes are remarkably tidy. If you are not close to one, it will not bother you. A black hole does not reach across space and pull you in. It does not send out death rays. It does not explode. It just sits there, warping space-time in its immediate vicinity, waiting for something to wander too close. Replace the sun with a black hole of identical mass, and Earth's orbit would not change. We would freeze in the dark, yes, because the sun's light and heat would be gone. But gravitationally, nothing would move. The black hole would hold the planets in their orbits exactly the way the sun does now. The danger zone around a black hole is localized. Get too close to the event horizon, within a few times the Schwarzschild radius, and tidal forces will rip you apart. Stay farther out, and you are fine. You can orbit a black hole safely for billions of years if you keep your distance. It is a passive threat, dangerous if you approach it, harmless if you do not. Magnetars are not passive. Magnetars do not wait for you to come to them. They announce their presence across light years with bursts of gamma rays and X-rays so intense that they can strip atmospheres, break apart molecules, and flood entire star systems with radiation. A magnetar does not need you to cross a boundary. It does not need you to fall in. It can reach out and touch you from distances that would be perfectly safe if the object doing the touching were a black hole. And that is the distinction that makes magnetars, in a very specific and very uncomfortable sense, more immediately dangerous than black holes. Let's be precise about what we mean by dangerous. A black hole will kill you if you get close enough, no question. The tidal forces near the event horizon, the difference in gravitational pull between your head and your feet, will stretch you into a thin stream of atoms long before you reach the horizon itself. Physicists call this spaghettification, which is a term that manages to be both technically accurate and deeply unsettling. For a stellar mass black hole, a few times the mass of the sun, spaghettification starts to become a problem at a distance of a few hundred kilometers from the event horizon. For a supermassive black hole, millions or billions of times the sun's mass, the tidal forces are weaker near the horizon because the horizon itself is so much larger. You could theoretically cross the event horizon of a supermassive black hole without even noticing, at least not right away. You would not be ripped apart until you got much closer to the singularity at the center. But either way, the danger is local. You have to be near the black hole for it to hurt you. A magnetar, on the other hand, does not need you to be near it. A magnetar can hurt you from across the galaxy. Not with gravity, with light, with radiation, with bursts of gamma rays carrying so much energy that they can punch through planetary atmospheres and chemically alter the air you breathe. The December 2004 flare from SGR 1000 806-20 was detected from 50,000 light-years away, and it was bright enough to measurably compress Earth's ionosphere. That is not a localized effect. That is a weapon with a range measured in tens of thousands of light-years, and Earth was not even close to the danger zone. We were well outside it. The burst was diluted by distance to the point where it was merely record-breaking instead of catastrophic. Move Earth closer, within a few thousand light-years, and the same burst would have been an extinction event. The kill radius around a magnetar is not defined by an event horizon. It is defined by how far away you need to be before a giant flare will not sterilize your planet. And that distance, based on the observed energies of magnetar flares and models of how gamma rays interact with planetary atmospheres, is somewhere in the neighborhood of 10 light-years. Maybe a bit more, maybe a bit less, depending on the specifics of the flare and the planet in question. But the number that keeps appearing in the literature is 10 light-years. Inside that radius, a giant magnetar flare is a civilization-ending event. Outside that radius, it is a spectacular light show that might cause some minor atmospheric disruption. The boundary is not sharp, it is not a wall, but it is real, and it is vastly larger than the danger zone around a black hole. 10 light-years is an enormous distance. For context, the nearest star to our Sun, Proxima Centauri, is about 4 light-years away. 10 light-years encompasses dozens of star systems. If a magnetar were sitting at the center of a sphere with a radius of 10 light-years, every planet in every system within that sphere would be at risk, not from gravity, not from being pulled in and crushed, from radiation, from gamma rays and X-rays flooding the atmosphere, breaking apart ozone molecules, creating nitrogen oxides, letting ultraviolet light from the parent star reach the surface unchecked. The ozone layer is not optional. Without it, surface life as we know it cannot exist. Plants die, plankton die. Anything that cannot hide underground or underwater is exposed to radiation levels that cause widespread DNA damage. Food chains collapse, ecosystems fail, and all of this can happen from a single burst lasting a fraction of a second, originating from an object tens of trillions of miles away. Black holes do not do this. A black hole sitting 10 light-years from Earth would be gravitationally uninteresting. It would tug on the Sun slightly, perturb the orbits of distant comets, and contribute to the overall mass budget of the local neighborhood. But it would not threaten us. It would not send out bursts of radiation. It would not strip our atmosphere. It would just be there, invisible unless something happened to fall into it and heat up enough on the way in to emit X-rays. Even then, the X-rays would be steady and relatively weak, nothing like a magnetar flare. A black hole 10 light-years away is a curiosity. A magnetar 10 light-years away is a countdown timer to extinction. This is not to say black holes are safe. They are not. But their danger is confined to a small region of space. Once you are outside that region, a black hole is no more threatening than any other massive object. It pulls on you with gravity. You pull back. The universe continues. A magnetar, by contrast, is dangerous across an entire volume of space thousands of times larger. Its danger is not gravitational, it is radiative. And radiation does not care about distance the way gravity does. Gravity falls off with the square of the distance. Double the distance, and the gravitational pull drops to 1/4. Radiation also falls off with the square of the distance, but the initial brightness of a magnetar flare is so absurdly high that even after being diluted by tens of thousands of light years, it is still bright enough to affect planets. That is the key difference. A black hole's influence drops off quickly. A magnetar's influence, when it decides to flare, reaches far. There is another layer to this. A black hole, once it has formed, is predictable. It has a mass, a spin, and possibly an electric charge. Those three numbers completely describe the black hole's external properties. This is summarized by a phrase in general relativity known as the no-hair theorem. Black holes have no hair, meaning they have no additional features, no bumps, no irregularities, no details, just mass, spin, and charge. You can calculate exactly how the black hole will behave based on those three numbers. Its event horizon has a specific size. Its gravitational field has a specific shape. It does not change unless something falls in and adds more mass or angular momentum. A black hole is stable. It sits in space and does its thing, which is mostly just existing and occasionally eating. Magnetars are not stable. A magnetar's magnetic field is constantly evolving. The field is twisted up by the star's rotation and by currents flowing through its interior. Stress builds up in the crust over years or decades. Then, without warning, the crust cracks. The magnetic field reconnects. A burst of gamma rays floods outward. The whole process is unpredictable. We cannot calculate when a magnetar will flare. We cannot predict how bright the flare will be. We know the mechanism. We understand the physics, at least in broad strokes. But we cannot forecast the events the way we can forecast an eclipse or the return of a comet. Magnetars are chaotic. They operate on timescales we can observe but not control, and the triggers for their outbursts are buried inside the neutron star where we cannot see them. That unpredictability adds a layer of menace that black holes do not have. A black hole is a known danger. You can see it coming, in the sense that you can measure its position, track its motion, and stay out of its way. A magnetar is a known danger that can suddenly get much worse without warning. One day, it is sitting quietly, spinning down, radiating a steady glow of X-rays. The next day it cracks, and for a tenth of a second, it is the brightest object in the sky in gamma rays. If you are close enough, that tenth of a second is all it takes. There is no evacuation plan. There is no early warning system. The light from the flare travels at the speed of light, so by the time you know it is happening, it has already happened. The gamma rays are already hitting your planet. The damage is already done. It is worth pausing to consider what that damage actually looks like. Gamma rays, when they hit an atmosphere, interact with nitrogen and oxygen molecules. The high-energy photons knock electrons off the atoms, creating ions. Those ions react with each other, forming new molecules that were not there before. One of the most important reactions involves nitrogen oxides. Gamma rays split nitrogen and oxygen molecules, and the resulting fragments recombine into nitrogen oxides, which are chemically reactive. Nitrogen oxides are effective at destroying ozone. One nitrogen oxide molecule can break apart hundreds of ozone molecules before it is removed from the atmosphere. So a gamma ray burst does not just blast the atmosphere with radiation and move on. It chemically alters the atmosphere, creating compounds that continue to deplete the ozone layer for years after the initial burst has faded. The ozone layer sits in the stratosphere, roughly 15 to 35 kilometers above the surface. It absorbs most of the sun's ultraviolet radiation, particularly the shorter wavelengths that are most damaging to DNA and organic molecules. Without the ozone layer, UVB and UVC radiation reach the surface at levels high enough to cause widespread harm. plants, which cannot move to shaded areas, are particularly vulnerable. Photosynthesis is disrupted, growth rates drop, some species die outright. Marine ecosystems are even more fragile. Phytoplankton, the base of the ocean food chain, are extremely sensitive to ultraviolet light. A significant increase in surface UV would crash plankton populations, which would cascade up the food web, collapsing fisheries and starving the larger animals that depend on them. On land, animals with exposed skin or eyes would suffer. UV radiation causes cataracts, skin cancers, and immune system suppression. Humans could survive by staying indoors or wearing protective clothing, but agriculture would be devastated. Crops would fail. Livestock, grazing in open fields, would develop cancers and eye damage. The global food supply would collapse within a growing season. And all of this would be triggered by a burst of gamma rays lasting less than a second, arriving from a magnetar that might be thousands of light years away. The most detailed modeling of this scenario was done in the early 2000s, before the December 2004 magnetar flare, but after astronomers had begun to understand what magnetars were capable of. Researchers ran simulations of gamma-ray bursts hitting Earth's atmosphere, calculating how much ozone would be destroyed and how long it would take for the ozone layer to recover. The results were grim. A nearby magnetar flare, from a distance of around 10 light-years, would deplete the ozone layer by 50% or more. Recovery would take years, during which time the surface would be bathed in elevated UV. The extinction rate among surface-dwelling species would spike. The fossil record contains at least one unexplained extinction event, the late Ordovician mass extinction about 450 million years ago, that matches the pattern you would expect from a gamma-ray burst or a magnetar flare. No smoking gun, no definitive proof. But the timing, the species affected, and the lack of other obvious causes make it plausible. A magnetar flare could have done it. We will never know for certain, but the possibility sits there, uncomfortable and unresolved. Black holes do not leave that kind of ambiguity in the fossil record. If a black hole had wandered close to Earth in the past, we would know. The gravitational disruption would have affected the orbits of planets. The sun's motion through the galaxy would have been perturbed. There would be evidence in the dynamics of the solar system itself. A magnetar flare, by contrast, leaves no gravitational trace. It is a pulse of light. It hits, it damages, and it moves on. The only evidence would be a sudden spike in extinction rates, and maybe, if you are very lucky, some chemical signature in ice cores or sediment layers showing an increase in nitrogen oxides. But those signatures degrade over time. After a few million years, they are gone. A magnetar flare in the distant past could have sterilized half the planet, and we would have no way to prove it happened. Now compare that to the way black holes interact with their surroundings when they are actively feeding. Supermassive black holes at the centers of galaxies often have accretion disks, vast swirling structures of gas and dust spiraling inward toward the event horizon. As the material falls inward, it heats up due to friction, reaching temperatures of millions of degrees. That hot gas radiates X-rays, which can be detected from across the universe. In the most extreme cases, the black hole also launches jets, narrow beams of particles accelerated to nearly the speed of light and fired outward along the black hole's spin axis. Those jets can extend for thousands of light years, carving through intergalactic space, heating and ionizing everything in their path. But even those jets are directional. They shoot out along the poles. If you are not in the line of fire, they do not affect you. A supermassive black hole with active jets is dangerous if you happen to be sitting directly above or below it. If you are off to the side, the jets miss you entirely. The X-rays from the accretion disk spread out in all directions, but they are steady, not pulsed. They do not spike suddenly. You can see them coming, you can measure them. They are part of the environment. A planet orbiting a star in a galaxy with an active, supermassive black hole at the center is bathed in a higher than average background of X-rays, but that background is constant. Life can adapt to constant radiation levels. What life cannot adapt to is sudden, intense bursts. A magnetar flare is not a steady drizzle, it is a flash flood. Some astronomers have described magnetars as cosmic lighthouses, and the metaphor is apt but slightly misleading. A lighthouse is steady, predictable, designed to warn you away from danger. A magnetar is more like a lighthouse that occasionally explodes. Most of the time, it spins quietly, its beam of X-rays sweeping across space, marking its position. Then, without warning, the lighthouse detonates, flooding the entire region with light bright enough to blind every detector pointed in its direction. And then it goes back to spinning quietly, as if nothing happened. That unpredictability is what makes magnetars so unsettling. They do not follow a script. They do not give warnings. They just are. And sometimes they flare. There is one more point worth making, and it is subtle but important. Black holes are defined by what they hide. The event horizon is a boundary beyond which information cannot escape. Whatever happens inside the event horizon is unknowable to the outside universe. This has led to decades of debate about whether information is truly lost when it falls into a black hole, or whether it is somehow encoded in the Hawking radiation that the black hole emits over trillions of years as it slowly evaporates. The debate is unresolved. It sits at the intersection of quantum mechanics and general relativity, and both theories have something to say, but they do not agree. Black holes are mysterious because they hide things. They are sealed boxes. We can measure their mass, spin and charge, but we cannot see inside. The interior is cut off from us, not just practically but fundamentally, by the structure of space-time itself. Magnetars are the opposite. They are defined by what they reveal. A magnetar's magnetic field is so strong that it forces matter and light to behave in ways that do not happen anywhere else in the universe. The vacuum becomes birefringent. Atoms elongate. Magnetic reconnection releases energies that would require a supernova under normal circumstances. All of these effects are observable. We can measure them. We can test our theories against them. Magnetars are not hiding their physics. They are putting it on display, broadcasting it across the galaxy in the form of gamma rays and X-rays and pulsed emission. They are laboratories, natural experiments running at energy scales we cannot reproduce on Earth. And they are telling us things about the universe that we could not learn any other way. That is what makes magnetars valuable, scientifically. They are extreme, yes. Dangerous, yes. But they are also informative. Every burst, every pulse, every oscillation in the light curve carries information about the star's structure, its magnetic field, its rotation rate, its internal composition. Neutron stars are the densest stable objects in the universe, and their interiors are made of matter at nuclear density, a regime we do not fully understand. The equations of state, the mathematical descriptions of how matter behaves under those conditions, are uncertain. We have models, but we do not have experimental data. Magnetars give us that data, indirectly. By observing how they spin down, how they flare, how their surfaces cool, we can constrain the equations of state, narrow down the possible structures, and test our theories of nuclear physics. Black holes do not give us that. Black holes hide their interiors. Magnetars expose theirs, at least partially, through their behavior. So when we ask whether magnetars are more terrifying than black holes, the answer depends on what you mean by terrifying. If you mean which object is more dangerous to a planet full of life, the answer is clearly magnetars. They can hurt you from farther away. They can do it without warning. They can sterilize entire star systems with a single burst. Black holes, by contrast, are dangerous only if you get close, and getting close is optional. If you mean which object is more conceptually unsettling, more incomprehensible, more alien, then black holes probably still hold the title. They are singularities. They break space-time. They erase information, or at least they appear to. They represent the ultimate limit of physics, the point where our theories stop working. That is a different kind of terror, abstract, existential, less immediate, but more profound. But here is the thing. Magnetars are not incomprehensible. We understand them, at least in broad strokes. We know what they are. We know how they form. We know why they flare. We have the equations. What makes magnetars terrifying is not that they are mysterious. It is that they are explicable, and they are still capable of this. The physics is known. The processes are understood. And the result is an object that can release more energy in 1/10 of a second than our sun will produce over 100,000 years, bright enough to affect planetary systems across light years. That is not a breakdown of physics. That is physics working exactly as it should, pushed to the absolute limit of what the universe allows. And the limit, as it turns out, is far higher than we ever had reason to expect. Black holes are terrifying because they hide. Magnetars are terrifying because they reveal. And what they reveal is that the universe, when it wants to, can build weapons, not intentionally, not with purpose, but the result is the same. A magnetar is a cosmic gun loaded with 100,000 years of solar energy, and it can fire without warning. The only reason we are safe is that there are none close enough to matter. Not yet, not that we know of, but the galaxy is large. The census of neutron stars is incomplete, and somewhere out there, hidden in the noise, there might be a magnetar we have not found yet, spinning quietly, storing energy, waiting. And when it flares, we will see it. If we are lucky, it will be far enough away that the burst is just data. Another point on the light curve. Another entry in the catalogue. If we are not, if it is closer, if the geometry is wrong, then the flash will be the last thing this planet sees before the ozone layer collapses and the surface becomes uninhabitable. That is the difference between black holes and magnetars. Black holes wait for you. Magnetars do not. Nobody rings a bell when physics stops being theoretical. There's no ceremony when an object moves from the pages of a paper into the observational record. The process is messier than that. A satellite catches something strange. A graduate student notices a pattern in data that nobody asked them to look for. A detector saturates during what should have been a routine observation. And slowly, over years, sometimes decades, the community decides that the thing they've been arguing about in conferences actually exists. Magnetars spent more than a decade in that limbo. The theoretical framework existed. Duncan and Thompson had published their Magnetar model in 1992, laying out the physics of ultra-strong magnetic fields and explaining how neutron stars born under the right conditions could generate fields in the range of 10 to the 15th Gauss. The model was elegant. It solved problems. It explained why soft gamma repeaters and anomalous X-ray pulsars behaved the way they did. But a model, no matter how compelling, is not the same thing as proof. The model predicted that these objects should exist. Observations needed to confirm that they actually did. The first real breakthrough came in June 1998. A team led by Krisa Kuvaliatu at NASA's Marshall Space Flight Center was using the Compton Gamma Ray Observatory to study an object designated SGR 1900+14. This was one of the soft gamma repeaters that had been puzzling astronomers since the late 1970s. It sat in the constellation Aquila, roughly 20,000 light-years from Earth, and it had been producing sporadic bursts of gamma rays for years. Nobody knew what powered those bursts. The leading theories ranged from accretion off a binary companion to some exotic process involving fallback material from the supernova that created the neutron star. None of the explanations were particularly satisfying. Kuvaliatu's team pointed Compton at SGR 1900+14 and watched. Over the course of several months, they detected about 50 flashes, short bursts of gamma rays, each lasting a few tenths of a second. That part was not new. SGRs had been bursting for decades. What was new was that Compton's instruments were good enough to measure something nobody had been able to measure before: the timing. Not just when the bursts happened, but the precise rotation period of the neutron star itself. The measurement came back at about 5.16 seconds. The star was completing one full rotation every 5.16 seconds. That was slow, extremely slow by pulsar standards. Most pulsars spin hundreds of times per second. Even the slower ones typically rotate once every few tenths of a second. A rotation period of 5 seconds put SGR 1900+14 firmly in the slow end of the distribution. And the slowdown rate, the measurement of how quickly the rotation was decaying, was enormous. The star was losing rotational energy at a rate that could not be explained by ordinary pulsar mechanisms. The numbers only made sense if the neutron star had a magnetic field in the range of 10 to the 14th Gauss or higher, Magnetar range. This was not indirect evidence, this was a direct measurement. The rotation period and the slowdown rate combined gave you the magnetic field strength. The math was straightforward. Plug in the numbers and out comes the field, 10 to the 14th Gauss, maybe higher. The data pointed unambiguously at a magnetic field orders of magnitude stronger than any ordinary pulsar. Kuvaliatu's team published the results, and the Magnetar hypothesis moved from interesting idea to observationally supported framework. SGR 1900+14 was a Magnetar, not probably, not maybe, it was. The Compton observation was the crack in the dam. Once one Magnetar had been confirmed, the floodgates opened. Other teams went back to archival data from previous satellites, looking for similar signatures in other SGRs and AXPs. They found them. One by one, the soft gamma repeaters and anomalous X-ray pulsars that had been sitting in the catalogs for years were reclassified. They were not separate classes of objects. They were Magnetars at different stages of their lives. Young Magnetars, still actively bursting, got labeled as SGRs. Older ones, past their most violent phase, got labeled as AXPs. The distinction was not sharp, but the underlying physics was the same. Ultra-strong magnetic fields, slow rotation, sporadic bursts powered by magnetic reconnection. All of it consistent with the Duncan and Thompson model. By the early 2000s, the census of known magnetars was growing steadily. NASA's Swift satellite, launched in 2004, was particularly effective at finding new ones. Swift was designed to detect gamma-ray bursts from collapsing massive stars, but it also picked up magnetar flares almost as a side effect. Fermi, launched in 2008, added more. Integral, a European satellite, contributed observations in the hard X-ray and soft gamma-ray bands. Between them, these missions identified dozens of new candidates. Some were confirmed quickly, others took years of follow-up observations to pin down. The discovery of SGR J0501 plus 4516 in August 2008 is a good example of how the process worked. Swift detected a series of short bursts coming from a previously uncatalogued source in the constellation Cassiopeia. The bursts had all the hallmarks of a magnetar: short duration, high energy, no obvious counterpart in other wavelengths. Follow-up observations with the Rossi X-ray Timing Explorer measured the source's spin period at 5.76 seconds, with a rapid slowdown rate consistent with a magnetic field around 10 to the 15th Gauss. The source was confirmed as a magnetar within a few months. By late 2008, it was in the catalogue, officially recognized as one of the galaxy's extreme neutron stars. Another odd case was SGR J0418 plus 5729, discovered in June 2009. This one was unusual because it was dim. Most magnetars, when they are active, are bright enough to be detected from thousands of light-years away. SGR J0418 plus 5729 was faint, barely visible even to sensitive X-ray telescopes. Its rotation period was measured at 9.1 seconds, and its slowdown rate suggested a magnetic field around 10 to the 13th Gauss. That is still magnetar territory, but on the low end. The discovery proved that magnetars were not all created equal. Some had stronger fields than others, some were more active, some were quieter. The class had a range, and the boundaries were not as sharp as the early models had assumed. The timing measurements were critical because they provided a way to measure the magnetic field without needing to observe the field directly. You cannot point a telescope at a neutron star and see its magnetic field the way you can photograph its surface. The field is invisible. What you can measure is how the star spins and how fast it is slowing down. Those two numbers, combined with some basic physics about how rotating magnetic fields interact with their surroundings, give you the field strength. It is an indirect measurement, but it is solid. The technique had been used on ordinary pulsars for decades. Applying it to magnetars was straightforward once the rotation periods were measured precisely enough. But timing measurements also revealed something unexpected: magnetars glitch. A glitch, in pulsar physics, is a sudden change in the star's rotation rate. Most pulsars spin down smoothly over time, gradually losing angular momentum as they radiate energy into space. But occasionally, a pulsar will suddenly spin up slightly, jumping to a faster rotation rate in a matter of seconds or minutes. Then it resumes its gradual slowdown, but from a slightly different baseline. Glitches are thought to be caused by interactions between the neutron star's solid crust and its superfluid interior. The superfluid spins independently of the crust, and when the two occasionally couple, angular momentum is transferred from the superfluid to the crust, causing a brief speed-up. Magnetars glitch more than ordinary pulsars, a lot more, and their glitches are often tied to burst activity. In many cases, a magnetar will glitch right before or during a burst episode, suggesting that the two phenomena are connected. The leading explanation is that the glitch is caused by a starquake, a fracture in the neutron star's crust triggered by the buildup of magnetic stress. The fracture releases energy, some of which goes into accelerating the star's rotation and some of which goes into heating the surface and powering the burst. The timing signature and the burst signature are two sides of the same event. One is the mechanical response. The other is the electromagnetic response. Both are observable, and together they provide a more complete picture of what is happening inside the magnetar. Some magnetars also show anti-glitches, sudden slowdowns instead of speed-ups. These are rarer and harder to explain. The mechanism is still debated, but the leading idea involves changes in the magnetosphere, the region of twisted magnetic field surrounding the star. If the field suddenly reconfigures during a burst, the change in magnetic pressure can transfer angular momentum outward, slowing the star down instead of speeding it up. The effect is small, typically a change in rotation period of a few microseconds or less, but it is measurable, and it shows up in the timing data as a distinct signature that correlates with burst activity. A 2019 study analyzed the timing behavior of several magnetars over a span of more than a decade. The researchers found that only about 30% of observed glitches were directly associated with outbursts. The other 70% happened without any corresponding burst activity. That was surprising. It suggested that not every starquake is violent enough to produce a detectable burst, or that some glitches are caused by internal processes that do not involve the magnetic field at all. The result complicated the picture slightly, but it also showed that magnetars are more dynamic than the simple models had predicted. The crust is constantly stressed, constantly adjusting, and the star's rotation is constantly responding. Sometimes you see the burst, sometimes you just see the timing anomaly, and sometimes both. The timing irregularities also scale with magnetic field strength. A study published in 2012 looked at a large sample of pulsars and magnetars and calculated the timing noise for each one. Timing noise is a measure of how much the star's rotation rate fluctuates over time. Ordinary pulsars have low timing noise. Their spins are remarkably stable. Magnetars have much higher timing noise, and the level of noise correlates strongly with the measured magnetic field strength. The stronger the field, the more irregular the timing. That makes sense. A stronger magnetic field means more stress on the crust, more frequent starquakes, more interactions between the field and the star's interior. All of that feeds into the timing signature. The correlation is clear in the data, and it provides another piece of evidence that magnetars are defined by their magnetic fields, not by some other exotic property. Spectroscopy added another layer of confirmation. Spectroscopy is the technique of splitting light into its component wavelengths and analyzing the pattern of bright and dark lines that appear. Different elements and ions produce different patterns, so by studying the spectrum of a star or other object, you can determine what it is made of and what physical conditions it is experiencing. For magnetars, spectroscopy revealed absorption features in the X-ray spectrum that could only be explained by extremely strong magnetic fields. One of the clearest examples came from observations of 1E1207, 4-5209, a neutron star sitting in the remnant of a supernova that exploded about 10,000 years ago. X-ray observations with the XMM Newton satellite showed a series of absorption lines in the star's spectrum. The lines were broad and shifted to higher energies than you would expect from atoms in a weak magnetic field. The shift was consistent with electrons in the star's thin atmosphere being forced into highly quantized energy states by the presence of a magnetic field around 10 to the 14th Gauss. That is a direct spectroscopic signature of a magnetar strength field. You cannot fake it. The physics is well understood. The absorption features appear at specific energies that depend on the field strength. Measure the energies, plug them into the equations, and out comes the field. The result matched the timing measurements. The two independent methods agreed. The field was real. Not every magnetar shows clear spectroscopic features. Some are too dim. Some are too heavily obscured by dust. Some have spectra dominated by thermal emission from the cooling surface, and the absorption lines are washed out. But in the cases where the lines are visible, they provide unambiguous confirmation that the magnetic field is in the Magnetar range. And they allow astronomers to measure not just the strength of the field, but its geometry. The shape and spacing of the absorption lines depend on whether the field is dipolar, meaning it has a simple North Pole and South Pole configuration, or multipolar, meaning it has a more complex structure with multiple poles and loops. Most magnetars appear to have multipolar fields, at least near the surface. That is consistent with the idea that the field is twisted and tangled by the dynamo process that created it. Then there are the multi-wavelength campaigns. Magnetars are observed across the entire electromagnetic spectrum, from radio waves to gamma rays, and the most useful observations come from coordinated efforts where multiple telescopes watch the same object at the same time. One of the most successful of these campaigns targeted SGR 1935 plus 2154, a magnetar discovered in 2014. In October 2020, the object entered an active phase, producing dozens of bursts over the course of several weeks. Astronomers around the world mobilized. Swift, Fermi, NICER, Integral, and several ground-based observatories all pointed at the source. The campaign tracked the magnetar's behavior in real time, capturing bursts in X-rays, gamma rays, and even radio waves. The radio detection was particularly unexpected because magnetars are not supposed to produce strong radio emission. Most of them are radio quiet. But SGR 1935 plus 2154 turned on in the radio band during its outburst, producing brief, bright pulses that looked remarkably similar to the fast radio bursts that have been puzzling astronomers for more than a decade. The connection is still being worked out, but the observation strongly suggested that at least some fast radio bursts might be coming from magnetars in distant galaxies. That was a major result, and it came directly from the multi-wavelength campaign. Gravitational wave searches have so far come up empty, but that does not mean they are not worth doing. Gravitational waves are ripples in spacetime produced by the acceleration of massive objects. The most famous sources are merging black holes and merging neutron stars, but in principle, any asymmetric motion of mass can produce gravitational waves. A starquake on a magnetar could produce a brief burst of gravitational waves if the fracture caused the star's shape to change suddenly. The waves would be weak, far weaker than the signal from a binary merger, but they might be detectable if the magnetar was close enough and if the starquake was violent enough. Several searches have been conducted using data from the LIGO, Virgo, and CAGRA detectors. One search, published in 2021, looked for gravitational wave signals coinciding with gamma-ray bursts from known magnetars. The search covered several giant flares, including the December 2004 event from SGR 1806-20. No gravitational waves were detected. The non-detection is not surprising. The predicted signal is extremely weak, and the detectors are only just beginning to reach the sensitivity needed to have a realistic chance of detecting something. But the null result is still useful. It places upper limits on how much energy could have been emitted as gravitational waves during the flares, which constrains models of how starquakes and magnetic reconnection happen. Future detectors will do better. A study published in 2020 calculated that if a magnetar underwent a giant flare within our own galaxy, and if just 1% of the flare's electromagnetic energy were emitted as gravitational waves, the signal would be detectable by the next generation of gravitational wave observatories. 1% is a lot, Most models predict the gravitational wave emission would be far below that. But the calculation shows that detection is at least plausible. A galactic magnetar flare bright enough and close enough might produce a gravitational wave signal that future instruments could catch. If that happens, it would open an entirely new window onto magnetar physics. Gravitational waves carry information about the star's internal structure, the shape of the crust, the way mass is distributed inside. None of that information is accessible through electromagnetic observations alone. A gravitational wave detection from a magnetar would be transformative. The recurring challenge with magnetars is that they are unpredictable. You cannot schedule observations the way you can with eclipsing binary stars or transiting exoplanets. Magnetars burst when they feel like it, and the bursts can be separated by days, months, or years. Most of the time, a magnetar is quiet, radiating a steady glow of X-rays that does not change much. Then, without warning, it wakes up. The crust cracks, the field reconnects, bursts flood out, and then it goes quiet again. If you happen to have a telescope pointed at it during the active phase, you get data. If you do not, you miss the event entirely. That makes magnetar science frustratingly dependent on luck and on rapid response systems that can retarget telescopes quickly when a burst is detected. SWIFT was designed specifically to handle this. The satellite carries a gamma-ray detector that scans the sky continuously, looking for transient sources. When it detects a burst, the satellite autonomously slews its X-ray telescope to point at the source within seconds. That quick response time is critical for catching the early phases of a magnetar outburst, when the emission is brightest and the light curve carries the most information. Other missions have followed similar strategies. Fermi, Integral, and the Chinese Hard X-ray Modulation Telescope all have rapid response capabilities. Together, they form a network that can catch magnetar bursts and coordinate follow-up observations across multiple wavelengths. But even with that network, most magnetar bursts are still missed. The sky is large. The satellites are looking in specific directions at any given moment. And magnetars are scattered across the galaxy, often hidden behind layers of dust that block optical light and even some X-rays. You need to be lucky. The burst has to happen when a satellite is looking in the right direction, or at least close enough that the satellite can slew quickly. And the magnetar has to be bright enough that the burst stands out above the background. Faint bursts from distant magnetars often go unnoticed, buried in the noise. The catalogue of known magnetars, as comprehensive as it has become, is still incomplete. There are almost certainly magnetars out there that have never been detected because they have not produced a burst bright enough or at a time when anyone was watching. Distance is part of the problem. Most known magnetars are thousands of light-years away. A few are in nearby galaxies, the Large and Small Magellanic Clouds, which sit about 160,000 and 200,000 light-years from Earth. One is in the Andromeda Galaxy, more than 2 million light-years away, though that detection is tentative and based on a single flare. The farther away the magnetar, the fainter its emission appears from Earth. Inverse square law. Double the distance, and the brightness drops to 1/4. A magnetar in the Large Magellanic Cloud has to be more than 100 times brighter than a magnetar in our own galaxy at a distance of a few thousand light-years to produce the same signal at Earth. That limits what we can detect. Only the brightest flares from the most distant magnetars make it into the catalogue. The faint ones, the small bursts, the brief hiccups in emission, those are lost to distance. And then there is the fact that magnetars, by their nature, do not last long in their active phase. The magnetic field is decaying. Energy is leaking out as radiation and as heat. A magnetar born today with a field of 10 to the 15th Gauss will have a field of 10 to the 14th Gauss in about 10,000 years. After a few tens of thousands of years, the field has decayed enough that the star stops producing dramatic bursts. It is still a neutron star. It is still rotating. It might still have a magnetic field stronger than any ordinary pulsar, but it is no longer a magnetar in the observational sense. It no longer bursts. It no longer announces itself. It fades into the background population, indistinguishable from the thousands of other neutron stars scattered through the galaxy, unless you happen to catch it at just the right moment with just the right instrument. That means the active magnetar population at any given time is a small fraction of the total number of neutron stars that were born as magnetars. Most of them have already aged out. They are still out there, spinning quietly, but they are no longer producing the signals that make them easy to detect. The census we have, the few dozen magnetars currently in the catalogue, represents only the youngest, most recently born members of the class. The rest are hidden, either too old, too faint, or too far away to have shown up yet. The true number of magnetars in the galaxy could be in the thousands, maybe more. We will never know for certain unless we find a way to detect the quiet ones, the ones that are not bursting. And right now, there is no clear path to doing that. You need the bursts. Without them, a magnetar looks like any other dim neutron star, and there are too many neutron stars to check them all. So where does that leave us? The evidence for magnetars is overwhelming. The timing measurements show rotation periods and slowdown rates that require magnetic fields in the 10 to the 14th to 10 to the 15th Gauss range. The spectroscopy shows absorption features consistent with those fields. The burst behavior, the light curves, the multi-wavelength observations, all of it points to the same conclusion. Magnetars are real, they exist, they are not theoretical constructs. They are observable astrophysical objects, catalogued, measured, studied. The framework that Duncan and Thomson proposed in 1992 has been validated by more than 3 decades of observations. Every prediction the model made has been confirmed. The spin periods, the slowdown rates, the burst energies, the connection between starquakes and magnetic reconnection, all of it checks out. But confirmation is not the same as understanding. We know magnetars exist. We know what they are. We have measured their properties, but we still do not fully understand how they work. The internal structure of a neutron star at nuclear density is not something we can replicate in a laboratory. The equations of state, the mathematical descriptions of how matter behaves under those conditions, are still uncertain. The details of how magnetic fields twist and reconnect in a neutron star's magnetosphere are still being worked out. The connection between starquakes and burst activity is understood in broad strokes, but the specifics, the precise triggers, the geometry of the reconnection regions, the timescales involved, all of that is still actively debated. And the gravitational wave searches, while so far unsuccessful, point to an entire dimension of magnetar physics that we have not accessed yet. Electromagnetic observations tell us what is happening on the surface and in the magnetosphere. Gravitational waves, if we can detect them, will tell us what is happening inside. They will reveal the star's shape, its internal mass distribution, the way the crust responds to stress. That is information we cannot get any other way. And it is the information we need if we want to move beyond confirming that magnetars exist and start answering the deeper questions about how they operate. The evidence is in. The case is closed. Magnetars are real, but the story is not over. Every new observation raises new questions, Every burst, every glitch, every spectroscopic feature adds another piece to the puzzle. And the puzzle, it turns out, is larger than anyone thought. Magnetars are not just neutron stars with strong magnetic fields. They are laboratories where quantum electrodynamics operates at energy scales we cannot reproduce on Earth. They are testing grounds for theories of nuclear matter. They are natural experiments in magnetic reconnection, starquakes, and radiative transfer. And they are objects that, by their very existence, push the boundaries of what physics allows. The evidence brought them out of theory and into reality. Now the real work begins. The evidence has brought magnetars out of theory and into reality. The timing measurements, the spectroscopy, the burst observations, the multi-wavelength campaigns, all of it confirms that these objects exist. They are real, they are catalogued, they are measured. But confirmation is only the beginning. The deeper you look at a magnetar, the stranger it becomes. Because what sits inside one of these objects is not just dense matter held together by gravity. It is matter pushed so far beyond ordinary conditions that it stops behaving like matter in any recognizable sense. It becomes something else, a fluid with no viscosity, a conductor with no resistance, a state of matter that exists nowhere else in the universe except inside neutron stars, and magnetars, with their ultra-strong magnetic fields, push that state even further into regimes where our best theories start to show cracks. The core of a neutron star is not made of atoms. Atoms cannot exist at that density. At roughly 10 to the 14th grams per cubic centimeter, nuclear density, the pressure is so high that protons and electrons are crushed together, converting into neutrons and releasing neutrinos in the process. What you get is a ball of neutrons packed so tightly that they are essentially touching. One neutron pressed up against the next, all the way through, no space between them, no atomic structure. Just a sea of neutrons held together by the strong nuclear force, the same force that holds protons and neutrons together inside an atomic nucleus. Except here, the nucleus is the size of a city, 12 miles across. Hundreds of trillions of neutrons, all squeezed into a sphere you could drive across in 20 minutes. That density, that pressure, creates conditions that do not exist anywhere else in the observable universe. Not in the core of the Sun, which is only about 100 times the density of water. Not in the core of a white dwarf, which reaches densities around 1,000,000 times water. Not even in the moments before a supernova, when the collapsing core briefly reaches nuclear density before bouncing. The difference is duration. A collapsing core hits nuclear density for maybe a second before it either bounces and explodes or collapses further into a black hole. A neutron star sits at nuclear density for billions of years. It is not a transient state, it is stable. And that stability allows the matter inside to settle into configurations that require time to form. Exotic configurations that theoretical physicists have been arguing about for decades because we have no way to test them in a laboratory. One of those configurations is superfluidity. A superfluid is a state of matter where a liquid flows without any friction or viscosity, no resistance. Pour a superfluid into a container, and it will climb the walls, flow over the edge, and drip out the bottom, all without losing energy. It sounds like science fiction, but it is real. Helium becomes a superfluid at temperatures near absolute zero. Physicists have been studying superfluid helium in labs since the 1930s, and the phenomenon is well understood. It happens because, at very low temperatures, helium atoms condense into a single quantum state. a state where they all behave as one coherent entity rather than a collection of independent particles. The result is a fluid that moves without friction because there is nothing for individual particles to scatter off of. They are all part of the same quantum wave. Inside a neutron star, the neutrons are not atoms, and the temperature is not near absolute zero. The surface of a newborn neutron star can be hotter than 1,000,000 degrees, but deep in the core, at densities above nuclear density, neutrons are predicted to form a superfluid anyway. Not because of low temperature, but because of high density. When neutrons are packed that tightly, quantum mechanics forces them to pair up. The pairing is mediated by the strong nuclear force, and it lowers the energy of the system. The paired neutrons condense into a coherent quantum state, and the result is a superfluid. A sea of neutrons flowing through the core of the star, with no viscosity, no friction, no resistance to motion. The neutrons move as one, a single quantum fluid occupying the entire core. The protons inside the core are predicted to do something even stranger. Protons, being charged particles, can pair up and form a superconducting state. Superconductivity is the phenomenon where an electrical current flows through a material with zero resistance. Ordinary conductors, like copper wire, have resistance. Electrons moving through the wire collide with atoms, lose energy, and generate heat. That is why electrical wires get warm when you run a current through them. A superconductor has no resistance. Electrons flow through it without losing energy. No heat, no loss. The current can circulate forever without decaying. Superconductivity happens in certain materials at very low temperatures, usually just a few degrees above absolute zero. The electrons pair up, forming what are called Cooper pairs, and those pairs move through the material as a coherent quantum state. Inside a neutron star core, protons are predicted to form Cooper pairs and become superconducting at densities slightly above nuclear density. The pairing mechanism is different from the one in ordinary superconductors. It is mediated by the strong nuclear force rather than by interactions with the crystal lattice of the material. But the result is the same. A superconducting proton fluid threading through the neutron superfluid, carrying currents with no resistance. And those currents, because they have no resistance, can persist for millions of years. Once a current gets started, it keeps going. It does not decay. It does not dissipate. It just flows. That has enormous implications for magnetars. Magnetic fields are generated by electrical currents. In an ordinary star, the currents are driven by convection and differential rotation, and they decay over time as the material resists the flow. In a magnetar, if the core is superconducting, the currents generating the magnetic field have no resistance. They can flow forever. The magnetic field does not decay because the currents do not decay, or at least the decay is much slower than it would be in a normal conductor. This is one of the leading explanations for why magnetar magnetic fields are so strong and so long-lived. The superconducting proton fluid locks the field in place, preserving it over timescales of thousands of years. But superfluidity and superconductivity also complicate the picture. If the neutrons in the core are a superfluid, they do not rotate the way ordinary fluids rotate. A normal fluid, when you spin it, develops a smooth velocity gradient. The fluid near the edge of the container moves faster than the fluid near the center, and the transition is continuous. A superfluid cannot do that. The quantum state does not allow for smooth velocity gradients. Instead, the superfluid breaks up into quantized vortices, tiny whirlpools where the fluid circulates in discrete units of angular momentum. Imagine a spinning bucket of water, except instead of a smooth swirl, the water is filled with millions of microscopic tornadoes, each one carrying a fixed amount of rotation. That is what a rotating superfluid looks like. And inside a neutron star, those vortices thread through the core in a dense array, pinned to the solid crust by magnetic forces and nuclear interactions. When a magnetar glitches, when its rotation rate suddenly changes, the leading theory is that the vortices in the superfluid core are unpinning and repinning. The superfluid, which was rotating slightly faster than the crust because it is decoupled from the outside world, suddenly couples to the crust through the vortices. Angular momentum is transferred, the crust spins up, the superfluid spins down, and we see the glitch in the timing data. The process happens on timescales of seconds to minutes, which is absurdly fast for an object containing more mass than the Sun. The fact that it happens at all is evidence that the core is not ordinary matter. Ordinary matter cannot transfer angular momentum that quickly across city-sized distances. A superfluid can. The problem is that we cannot see inside a neutron star. We cannot drill a hole and take a sample. We cannot send a probe down into the core. All we have are models, equations of state that describe how matter behaves at nuclear density and beyond. And those equations are uncertain. We know the basic physics. We know quantum chromodynamics, the theory that describes how quarks and gluons interact to form protons and neutrons, and how neutrons interact with each other through the strong nuclear force. But QCD, as it is called, is notoriously difficult to calculate at the densities and pressures relevant to neutron star cores. The equations are solvable in principle, but in practice you need enormous computational resources, and even then the results come with large uncertainties. Different equations of state make different predictions about what happens inside a neutron star. Some predict that the core remains mostly neutrons, with a small fraction of protons and electrons mixed in. Others predict that at the highest densities, near the center of the most massive neutron stars, the neutrons themselves break apart into their constituent quarks, forming what is called quark matter. Quark matter is a soup of up quarks, down quarks, and strange quarks, no longer bound into protons or neutrons, just a sea of quarks interacting directly with each other. It is the closest thing to the state of matter that existed in the first microseconds after the Big Bang, when the universe was so hot and dense that protons and neutrons had not yet formed. Whether quark matter actually exists inside neutron stars is an open question. Some equations of state allow for it, others do not. The answer depends on details of the strong nuclear force that we do not yet fully understand. Magnetars, because of their extreme magnetic fields, provide a way to test these equations of state. The magnetic field affects the structure of the star. It adds pressure, it changes the way particles move, and it alters the star's radius and moment of inertia in ways that depend on the equation of state. Measure the star's mass, radius, and moment of inertia, and you can rule out certain equations of state and favor others. The challenge is making those measurements. Mass can be determined if the magnetar is in a binary system, which most are not. Radius can be inferred from X-ray observations if you can model the surface emission accurately, which is difficult because the emission is affected by the magnetic field and by the star's rotation. Moment of inertia can be calculated from glitch observations, but only if you know how much angular momentum was transferred during the glitch, and that depends on assumptions about the superfluid and the vortex dynamics. Each measurement is indirect. Each relies on a chain of assumptions, and each has error bars, but taken together, the observations are starting to narrow the range of possible equations of state. A 2024 analysis combined timing data from several magnetars with X-ray spectroscopy and glitch observations and concluded that the equation of state must be stiff, meaning the neutron star material resists compression more strongly than softer models predict. A stiff equation of state implies that neutron stars have larger radii, and that quark matter, if it exists at all, only appears in the most massive neutron stars, not in the typical 1.4 solar mass objects. That is a tentative conclusion, and it will be refined as more data come in. But it shows that magnetars are not just interesting objects to observe, they are laboratories. Natural experiments running at energy scales we cannot reproduce on Earth, probing physics we cannot test any other way. General relativity gets tested here too. Neutron stars are the most extreme gravitational environments in the universe that are not black holes. The gravitational field at the surface of a neutron star is about 2 × 10⁻11 stronger than Earth's gravity. Strong enough that time itself runs slower. A clock sitting on the surface of a neutron star would tick measurably slower than a clock far from the star. The difference is not huge, but it is real, and it shows up in observations. Photons climbing out of the neutron star's gravitational well lose energy, shifting to longer wavelengths. This is called gravitational redshift, and it is a direct prediction of general relativity. Measure the redshift, measure the star's mass and radius, and you can test whether the observed redshift matches what general relativity predicts. The strongest test of general relativity from a magnetar came in 2026. Astronomers reported observing what they called a chirp in the light curve of a newborn magnetar, a signal that appeared in the first few seconds after the neutron star formed, and that was consistent with the emission of gravitational waves as predicted by general relativity. The interpretation is still being debated, but if confirmed, it would be the first direct observation of a general relativistic effect tied to a magnetar's birth. The chirp, a rapid oscillation in brightness, was caused by the star's rotation interacting with spacetime in a way that only general relativity allows. The effect is tiny, lasting only fractions of a second, but it was bright enough and distinct enough that the instruments caught it. The result has not been independently verified yet, and the error bars are large, but it points to a future where magnetars are used not just to test equations of state, but to test the very framework of spacetime itself. Then there are the exotic particles. Axion-like particles, or ALPS, are hypothetical particles predicted by certain extensions of the standard model of particle physics. The standard model is the theory that describes all known particles and forces except gravity. It is extraordinarily successful, tested to absurd precision in particle accelerators and other experiments. But it has gaps. It does not explain dark matter. It does not explain why the strong nuclear force appears to conserve a symmetry called charge parity, or CP symmetry, even though there is no obvious reason it should. Axions were invented to solve that second problem. They are light, weakly interacting particles that, if they exist, should be produced in large numbers inside stars and in the early universe. Axion-like particles are a broader class of particles with similar properties, but not necessarily tied to the specific CP problem. They interact very weakly with ordinary matter, which is why they have never been detected directly. But in environments with extremely strong magnetic fields, like the magnetosphere of a magnetar, ALPS can convert into photons. The process is called the Primakoff effect, and it happens because the magnetic field mediates the conversion. An ALP traveling through the field can, with some probability, turn into a photon. The photon is real, observable, and it carries energy away from the star. If magnetars produce ALPS in their cores, And if some of those ALPs convert into photons in the magnetosphere, we should see an excess of X-ray and gamma-ray emission that cannot be explained by thermal cooling or magnetic field decay alone. A 2021 study explicitly framed magnetars as probes of axion-like particles. The researchers calculated how many ALPs a magnetar core should produce, assuming various coupling strengths to protons and neutrons. They then modeled how those ALPs would travel outward through the star, escape into the magnetosphere, and convert into photons in the magnetic field. The conversion is most efficient in a specific energy range, roughly 100 kilielectron volts to 1 megaelectron volt, and at distances up to about 3 stellar radii from the surface. The study concluded that existing X-ray observations of magnetars could be used to constrain the coupling strength of ALPs to nucleons. If the coupling is too strong, the magnetar would cool too quickly, radiating away energy as ALPs faster than observations allow. If the coupling is too weak, no ALPs are produced and the magnetar cools normally. The observed cooling rates sit in between, which means ALPs, if they exist, must have coupling strengths within a specific narrow range. The calculation depends heavily on the equation of state and on whether the protons in the core are superconducting. Superconductivity changes the rate at which ALPs are produced because it affects how protons interact with each other and with the neutrons around them. A superconducting core produces fewer ALPs than a normal core, which shifts the constraints. Different assumptions about superfluidity and superconductivity lead to different conclusions about the allowed parameter space for ALPs. The result is not a detection, it is a constraint. Magnetars have not proven that ALPs exist, but they have narrowed the range of properties ALPs can have if they do exist. That is still valuable. Particle physicists building theories need constraints. Magnetars provide them. The conversion of ALPs into photons in the magnetosphere is also testable. If the conversion is happening, the emitted photons should have specific spectral features and polarization properties that depend on the magnetic field geometry and the ALP particle mass. A 2024 paper modeled this in detail and predicted that certain magnetars, depending on their field strength and viewing angle, should show an excess of emission in the hundreds of kiloelectron-volt range with a distinct polarization signature. Observations with future X-ray polarimeters could confirm or rule out the effect. IXPE, the Imaging X-ray Polarimetry Explorer, launched in 2021, is already observing magnetars and collecting polarization data. The results are still being analyzed, but preliminary findings show that some magnetars have polarization properties that are harder to explain with standard models than others. Whether that is evidence for ALPs or just evidence that magnetospheres are more complicated than we thought is still unclear. Dark matter is another exotic possibility. Dark matter, whatever it is, makes up about 85% of the matter in the universe. We know it exists because we can measure its gravitational effects on galaxies and galaxy clusters, but we do not know what it is made of. The leading candidates are weakly interacting massive particles, or WIMPs, and axions, which are a type of ALP. If dark matter is made of WIMPs or axions, those particles should be everywhere, including inside and around neutron stars. A 2025 study explored how a dark matter halo surrounding a magnetar could alter its structure, rotation rate, and gravitational wave emission. The calculation assumed that dark matter interacts with ordinary matter only through gravity, no other forces. Even with that minimal interaction, the presence of a dark matter halo changes the star's moment of inertia and shifts its spin period slightly. The shifts are small, but they are potentially measurable if you have precise timing data. The dark matter Magnetar model is speculative. It relies on assumptions about the dark matter particle mass, its density distribution around the star, and the equation of state of the neutron star itself. Change any of those assumptions and the predicted effects change. But the model shows that magnetars could in principle be used to probe dark matter in a way that does not require detecting the particles directly. You measure the star's rotation, compare it to what you would expect without dark matter, and see if there is a discrepancy. If there is, and if you can rule out other explanations like uncertainties in the equation of state or errors in the timing measurements, you have indirect evidence for dark matter interacting with the star. It is a long shot, but it is worth pursuing because the payoff, if it works, is enormous. A confirmed dark matter signal from a magnetar would be one of the biggest discoveries in physics. It would tell us what dark matter is made of, how it interacts, and how it affects astrophysical objects. That is worth a few speculative papers. Vacuum birefringence showed up earlier in this discussion, but it is worth returning to because it represents one of the few places where magnetar observations directly test quantum electrodynamics in a regime we cannot access on Earth. QED is the theory of how photons interact with charged particles, and it is one of the most precisely tested theories in all of physics. The predictions of QED match experimental results to better than 1 part in 10 billion in some cases, but those tests are done in weak magnetic fields far below the QED critical field of about 4.4 times 10 to the 13th Gauss. Magnetars have fields above that threshold, way above. And QED predicts that in such strong fields, the vacuum itself becomes polarized and starts to affect how light propagates. The effect was detected, or at least strongly suggested, in 2026 observations of Magnetar 1E1547-5408. The observations, made with IXPE, showed that the polarization of the X-rays emitted by the magnetar was rotating as the light traveled outward through the magnetosphere. The rotation was consistent with the light passing through a birefringent vacuum, where the two polarization modes traveled at slightly different speeds, and the polarization vector precessed as a result. The signal was not unambiguous. There are other effects that can rotate polarization, including scattering in the thin atmosphere above the neutron star's surface and the geometry of the magnetic field itself. But the data analysis, as careful as the team could make it, suggested that vacuum birefringence was the dominant effect. If confirmed, it is the first direct observation of a quantum vacuum effect predicted by QED, but never before seen. That is a big deal. It is one thing to calculate an effect and predict it theoretically. It is another to see it happen in nature. The field is moving fast. The 2015 review, titled Magnetars, The Physics Behind Observations in Reports on Progress in Physics, laid out the state of the field at that time and served as the standard reference for nearly a decade. It covered the basics of magnetar structure, the burst mechanism, the cooling history, the connections to supernovae and gamma-ray bursts. It was comprehensive, but in the 10 years since that review was published, the observational landscape has changed dramatically. IXPE launched and started returning polarization data. Multi-wavelength campaigns caught magnetars in the act of bursting and linked some of them to fast radio bursts. The first magnetar birth was observed in real time, or at least inferred from the light curve of a supernova. Gravitational wave searches began. Dark matter and axion models were developed and tested against real data. The field did not just grow, it exploded. The number of open questions has multiplied, and the tools available to answer them have gotten sharper. The unifying theme is that magnetars are natural laboratories. They reach conditions we cannot create on Earth. They probe physics at energy scales and field strengths that would require particle accelerators the size of solar systems. They test general relativity in strong field regimes. They constrain exotic particles. They reveal the properties of matter at nuclear density, and they do all of this passively. We do not have to build them. We do not have to fund them. We just have to watch. Point the telescopes, collect the data, analyze the light curves, measure the polarizations, build the models, compare the predictions to the observations, and slowly, piece by piece, the physics emerges. But the work is hard because the systems are complicated. A magnetar is not a simple object. It is a rotating, magnetized, superfluid, superconducting ball of nuclear matter wrapped in a thin crust, threaded with quantized vortices, surrounded by a twisted magnetosphere that periodically reconnects and dumps enormous amounts of energy into space. Every part of that system interacts with every other part. The rotation couples to the magnetic field through the crust. The magnetic field couples to the superfluid through the vortices. The superfluid couples to the proton superconductor through nuclear forces. The emission we see is the result of all of those interactions playing out simultaneously. Untangling them requires detailed models and high-quality data, and even then, the results come with caveats. The models rely on assumptions about the equation of state, the field geometry, the particle physics, the general relativistic corrections. Change one assumption and the conclusions shift. That is why the field is still so active, because the measurements are hard, because the theory is uncertain, because every new observation opens up new possibilities and rules out others. Magnetars are not a solved problem. They are a frontier, and the frontier is moving. The next generation of X-ray telescopes, the next round of gravitational wave detectors, the next multi-wavelength campaigns, all of them will push deeper into magnetar physics and bring back more data, more constraints on the equation of state, more tests of general relativity, more searches for axions and dark matter, more evidence for or against vacuum birefringence, and eventually, maybe, a coherent picture of what actually happens inside one of these objects when the crust cracks and the field reconnects and 100,000 years of sunlight floods into space in the span of 1/10 of a second. For now, the answer is incomplete. We know enough to say that magnetars are real, that they operate in a regime where fundamental physics is being tested, and that the results so far are consistent with our best theories, but also pushing those theories to their limits. QED works, even at 10 to the 15th Gauss, at least as far as we can tell. General relativity works, even in gravitational fields 2 times 10 to the 11 times stronger than Earth's. The standard model holds, though it leaves room for particles we have not detected yet. The equations of state are still uncertain, but the range of possibilities is narrowing. And the superfluid and superconducting phases inside the core, while not directly observable, are indirectly confirmed by the glitches and the cooling rates and the magnetic field decay timescales. The pieces fit, not perfectly, not yet. But they fit well enough that we can keep building on them, confident that the foundation is solid even if the details are still blurry. What magnetars are doing at their core is bending the rules, not breaking them. The laws of physics still apply, but they are being applied in a regime so extreme that the effects look unfamiliar. The vacuum glows, neutrons flow without friction, protons carry currents that last for millennia. Magnetic fields store enough energy to outshine galaxies, and all of it happens inside a sphere 12 miles wide, spinning once every few seconds, radiating X-rays into the dark. The rules are bent, yes, but they have not snapped, and that, in a strange way, is the most remarkable thing about magnetars. They push physics to the edge, and physics holds. So far. The evidence is in. The measurements are confirmed. The theory, while still incomplete, has passed every major test thrown at it. Magnetars are real. They exist. They operate at the edge of what physics allows, bending the rules without breaking them. And yet, after more than 3 decades of observations, after cataloguing dozens of these objects, after measuring their magnetic fields and their spin rates and their burst energies, we are still missing pieces, large pieces. The kind of pieces that determine whether we actually understand these objects or whether we are just describing them. That gap between description and understanding is where the future lives. And the future, it turns out, is being built right now. New telescopes are coming online, new detectors are being designed, new theoretical frameworks are being tested against simulations running on the most powerful supercomputers ever built. The next decade of magnetar research will not just refine what we already know, it will open entirely new windows onto phenomena we have only glimpsed so far. And some of those windows might reveal things we were not expecting. Things that force us to rethink not just magnetars, but the broader population of compact objects scattered through the galaxy. Start with the telescopes, because that is where the observational breakthroughs will come from. The Square Kilometre Array, usually shortened to SKA, is the largest radio telescope project ever attempted. When it is fully operational, sometime in the late 2020s, it will consist of thousands of individual radio antennas spread across 2 continents, South Africa and Australia, working together as a single instrument with a collecting area of roughly 1 square kilometre. That is about 250 acres of radio dishes, all pointed at the sky, all feeding data into a central processing system capable of handling exabytes of information per day. The sensitivity will be orders of magnitude better than any existing radio telescope. The frequency coverage will span from 50 MHz to 15 GHz, a range wide enough to catch everything from low-frequency pulsations to high-frequency bursts, and the time resolution, the ability to detect rapid changes in brightness, will be measured in tens of microseconds. That matters because some of the most interesting signals from neutron stars, including magnetars, happen on timescales shorter than a millisecond. SKA is being positioned as a fast radio burst hunter. Fast radio bursts, or FRBs, are one of the most mysterious phenomena in modern astronomy. They are brief, intense flashes of radio emission lasting just a few milliseconds, sometimes less. The first one was discovered in 2007, buried in archival data from the Parkes Observatory in Australia. For years, astronomers were not sure if FRBs were real or if they were just instrumental glitches. By the mid-2010s, enough events had been detected that the reality of the phenomenon was no longer in question. The mystery shifted to what was producing them. The brightness, the brevity, and the distances involved. Some FRBs come from galaxies billions of light-years away, pointed to extremely energetic processes, colliding neutron stars, evaporating black holes, supernova remnants, magnetars. The list of proposed explanations grew longer every year, and none of them could be ruled out because the data were too sparse. Then, in April 2020, an FRB was detected from within our own galaxy. The source was SGR 1935 plus 2154, a known magnetar sitting about 30,000 light-years from Earth. The burst was picked up by multiple radio telescopes simultaneously, and it was accompanied by an X-ray flare. That was the smoking gun. It proved, beyond reasonable doubt, that at least some FRBs are produced by magnetars, Not all of them. The jury is still out on whether every FRB has a Magnetar origin or whether there are multiple classes of progenitors. But the connection is real. Magnetars can produce FRBs. The mechanism is still being worked out, but the leading idea is that the radio burst is generated during magnetic reconnection events in the magnetosphere, possibly involving coherent emission from bunches of charged particles accelerated to nearly the speed of light. SKA will change the game because it will detect FRBs by the thousands, maybe tens of thousands. Current telescopes catch a few dozen per year, and most of those detections are one-offs. The source flashes once, and then it is gone. Repeating FRBs, the ones that flash multiple times from the same location, are rare. SKA, with its enormous sensitivity and its ability to scan large areas of the sky continuously, will catch repeaters routinely. It will measure their positions with enough precision to identify the host galaxies. It will track how the bursts evolve over time, whether they get brighter or dimmer, whether the intervals between bursts follow a pattern. And it will do all of this in the southern hemisphere, which has been underserved by radio telescopes compared to the north. That coverage matters because many of the brightest and most interesting FRB sources happen to sit in parts of the sky best observed from the south. The broader implication is that SKA will build a detailed census of FRB sources. Right now, we have a few dozen well-studied events. SKA will give us thousands, and buried in those thousands will be patterns, correlations between burst brightness and host galaxy type, connections between FRB rate and magnetar age, hints about what conditions are required for a magnetar to start producing radio bursts in the first place, because not all magnetars produce FRBs, most do not, as far as we can tell. The ones that do seem to be special in some way, and figuring out what makes them special is one of the key questions driving the field right now. One possibility raised in a 2024 modeling study is that many repeating FRBs come from magnetars in binary systems. The idea is that the magnetar is not alone. It has a companion star, possibly a massive star still burning hydrogen, possibly a lighter star, like a B star with a disk of gas surrounding it. The companion star feeds material into the magnetar's magnetosphere, either through a stellar wind or through mass transfer if the two stars are close enough. That material interacts with the magnetar's magnetic field, creating the conditions needed for coherent radio emission. The geometry matters. If the magnetar's spin axis, its magnetic axis, and the orbital plane of the binary are all aligned or nearly aligned, the radio beam sweeps past Earth regularly, and you see repeating bursts. If the alignment is off, you might only catch the magnetar during certain phases of its orbit, and the bursts look sporadic. The binary model is speculative, but it fits several pieces of data that have been hard to explain otherwise. Repeating FRBs often show changes in polarization and dispersion measure over time, suggesting that the environment around the source is changing. A binary companion with a wind or a disk could provide that changing environment. The model also predicts that FRB sources should be associated with regions of active star formation, which is where you find massive stars and binaries. And indeed, several well-studied FRB sources sit in or near star-forming regions in their host galaxies. The correlation is not perfect, but it is there. Testing the binary hypothesis requires finding magnetar companions. That is harder than it sounds. If the companion is a normal star, it should be visible in optical or infrared light. But magnetars are faint in those wavelengths, and the companion, if it is far enough away or small enough, might be too dim to detect. Observations are ongoing. A 2024 study searched for companions around 15 known magnetars and found 2 new candidate systems that looked like they might be remnants of disrupted binaries, systems where the supernova that created the magnetar also blew the companion away. 13 of the 15 magnetars were associated with supernova remnants, which is consistent with them being relatively young. The other 2 had no obvious remnants nearby, suggesting they might be older or that the remnants have faded below detectability. The search continues, and SKA, with its ability to map the environments around magnetars in radio wavelengths, will add more data. The broader question is whether FRBs can also come from other sources, black holes, for example. There is a long-standing theoretical interest in whether a magnetar orbiting a black hole could produce FRBs. The idea is that the black hole's gravity and the magnetar's magnetic field interact in complicated ways, possibly generating bursts of radio emission during close approaches or through tidal disruption of the magnetar's magnetosphere. The geometry would be extreme. The black hole could be stellar mass, a few times the Sun, or it could be intermediate mass, thousands of solar masses. Either way, the magnetar would be orbiting in a region where spacetime is severely warped, and the magnetic field lines would get twisted and stretched by the black hole's gravity. When those field lines reconnect, the energy release could be even more dramatic than in an isolated magnetar. The radio burst could be brighter, the time scale could be shorter, and the event might repeat on the orbital period, every few hours or days, depending on how close the 2 objects are. This is not confirmed. There is no observed magnetar black hole binary. But the idea has not been ruled out either. The FRB literature still treats black hole-based engines as plausible alternatives to magnetars, which keeps the possibility open. And if such a system exists, SKA will find it. The signature would be unmistakable. Repeating bursts on a strict clock tied to an orbital period. Brightness variations as the magnetar moves closer to and farther from the black hole. Possibly gravitational wave emission as the orbit decays. The system would be loud in every wavelength, from radio to X-rays to gravitational waves. It would be, in every sense, a multi-messenger source, the kind of object that every telescope in the world would point at the moment it was discovered. Then there is Athena. New Athena, technically, after the mission was rescoped in the early 2020s. Athena is a next-generation X-ray observatory being developed by the European Space Agency with contributions from NASA and other international partners. It is scheduled to launch in the early 2030s, and it will be the most powerful X-ray telescope ever flown. The mirror is enormous, with a collecting area several times larger than any previous X-ray mission. The instruments include a high-resolution spectrometer capable of measuring X-ray line profiles with unprecedented precision, and a wide-field imager that can track transient sources across large areas of the sky. Athena is being designed to study everything from supermassive black holes in distant galaxies to the hot gas in galaxy clusters. But one of its key science goals is to follow up on transient compact object events, including FRBs, magnetar flares, and possibly gravitational wave sources. The connection to FRBs is direct. Many FRB sources, particularly the repeating ones, are expected to be magnetars. If a magnetar produces an FRB, it might also produce an X-ray flare at the same time or shortly afterward. Athena will be able to detect those flares and measure their spectra in detail. The X-ray spectrum carries information about the magnetar's surface temperature, its magnetic field geometry, and the composition of its thin atmosphere. It also reveals whether the flare is powered purely by magnetic reconnection or whether there is some additional energy source, like accretion from a companion or fallback material from the supernova remnant. Athena's spectrometer can resolve individual absorption and emission lines in the X-ray spectrum, which older missions could not do. That resolution will allow astronomers to test models of magnetar atmospheres, measure the gravitational redshift directly, and search for signatures of exotic particles like axions converting into photons in the magnetosphere. Athena will also search for X-ray emission following gravitational wave events. When two neutron stars merge, they produce a burst of gravitational waves that can be detected by LIGO, Virgo, and Cagra. They also produce electromagnetic radiation, mostly in the X-ray and gamma-ray bands, as the newly formed remnant, which could be a hypermassive neutron star or a black hole, settles into a stable configuration. If the remnant is a magnetar, it will glow in X-rays as it cools and as its magnetic field interacts with the surrounding debris. Athena will be able to catch that emission, measure its evolution over hours to days, and determine whether the remnant is a stable neutron star or whether it collapses into a black hole after a few seconds. The X-ray data, combined with the gravitational wave signal, will provide a complete picture of what happens during and after a neutron star merger. That has implications not just for understanding magnetars, but for understanding the origin of heavy elements like gold and platinum, which are thought to be produced in these mergers. The forecast from a 2024 study suggested that with Athena and the next generation of gravitational wave detectors, astronomers could detect up to 1 magnetar remnant per year from neutron star mergers during current observation runs. Future interferometers with better sensitivity and broader frequency coverage could push that rate much higher. The key is catching the X-ray signal quickly, within hours of the gravitational wave detection, before the remnant fades below detectability. Athena is designed to do exactly that. It has rapid response capabilities that allow it to retarget within minutes of receiving an alert from the gravitational wave network. That responsiveness is critical because transient sources do not wait. You catch them in the act, or you miss them. Theoretical modeling is advancing in parallel with the observational campaigns. Simulations of magnetar magnetospheres are getting more sophisticated, incorporating general relativistic effects, quantum electrodynamics, and the full complexity of magnetic field geometries. A 2024 study used three-dimensional magnetohydrodynamic simulations to model how magnetic field lines twist and reconnect in a rotating magnetar magnetosphere. The simulation tracked individual field lines over multiple rotation periods and calculated where and when reconnection events should occur. The results showed that reconnection tends to happen in localized regions where the field lines are most twisted, and that those regions move around the magnetosphere as the star rotates. The pattern is not random. It is tied to the star's spin, its magnetic axis orientation, and the history of how the field was wound up in the first place. That structure shows up in the burst light curves as repeated peaks and dips, and it matches the observed timing patterns from several magnetars. Another simulation, published in early 2025, focused on the interaction between a magnetar and a companion star. The model assumed a magnetar with a field of 10 to the 15th Gauss orbiting a B star with a decretion disk. The disk is a flattened ring of gas fed by material ejected from the B star's equator. As the magnetar moves through the disk, the gas interacts with the magnetic field, creating shocks and heating the material to X-ray temperatures. The simulation predicted that this interaction should produce periodic X-ray flares tied to the orbital period, and that the flares should be accompanied by bursts of radio emission if the conditions are right for coherent emission, The predicted light curve matched the observed behavior of FRB 20201124A, a well-studied repeating FRB source. The match was not perfect, but it was close enough to suggest that the binary model is on the right track. These simulations are expensive. They require supercomputers running for weeks or months to produce a single model. But they are necessary because the physics is too complicated to solve analytically. You cannot write down a simple equation that describes how a twisted magnetic field reconnects in 3 dimensions while accounting for general relativistic effects and quantum corrections to the vacuum. You have to simulate it. You have to build the model, feed it the initial conditions, let it run, and see what comes out the other end. Sometimes the results match observations, sometimes they do not. When they do not, you adjust the model and try again. It is slow work, but it is the only way forward when the system is this complex. The philosophical dimension is harder to quantify, but impossible to ignore. Magnetars were not supposed to exist. That is not an exaggeration. When the first soft gamma repeaters were discovered in the late 1970s, nobody knew what they were. The objects did not fit into any existing category. They were not pulsars. They were not X-ray binaries. They were not supernova remnants. They were anomalies. And for more than a decade, they stayed that way, unexplained, catalogued but not understood. It took a theoretical leap, the Duncan and Thompson Magnetar model published in 1992, to even suggest that such objects could exist. And it took another 6 years, until the Compton observations in 1998, to confirm that the model was right. That progression from anomaly to hypothesis to confirmation is rare in astrophysics. Most of the time, observations come first, and theory scrambles to catch up. Magnetars were different. The theory arrived early, sat patiently, and waited for the data to prove it correct. That raises an uncomfortable question. If magnetars, objects that nobody predicted and that operate at the absolute edge of what physics allows, turned out to be real, what else is out there? What other impossible objects are sitting in the data, waiting for someone to notice them? The universe has a track record of building things that push right up against the limits of the possible. Black holes exist, even though the idea seemed absurd when it was first proposed. Neutron stars exist, even though the density required to make them was thought to be unattainable outside the first moments of the Big Bang. Dark matter exists, even though we have never detected a single particle of it directly. The lesson, repeated over and over, is that the universe does not care about human intuition. It builds what the laws of physics allow, and the laws of physics, it turns out, allow a lot more than we give them credit for. Magnetars are proof of that. They are objects that sit at the intersection of quantum mechanics, general relativity, nuclear physics, and plasma physics, all operating simultaneously at extremes we cannot replicate on Earth. They bend space-time. They polarize the vacuum. They store enough energy in their magnetic fields to power a star for 100,000 years. They flare without warning, releasing more energy in 1/10 of a second than our sun will radiate over millennia. And they do all of this while spinning once every few seconds, radiating X-rays, occasionally bursting in radio waves, and slowly decaying over thousands of years until they fade into the background population of ordinary neutron stars. They are, by every reasonable measure, the most extreme stable objects in the universe that are not black holes, and they exist, not in theory, in reality, scattered across the galaxy. Catalogued, measured, observed. The fact that magnetars exist and that they operate the way they do tells us something important about the universe itself. It tells us that the gap between impossible and merely improbable is smaller than we thought. It tells us that the laws of physics, when pushed to their limits, do not break. They bend, they stretch. They produce outcomes that look impossible from a distance, but that make perfect sense once you work through the equations. Magnetars are not violations of physics. They are physics taken to its logical extreme. And the extreme, as it turns out, is far stranger than the baseline. That strangeness is not going away. The next generation of observations will only deepen it. SKA will find thousands of FRBs and link many of them to magnetars, but it will also find events that do not fit the magnetar model. Athena will measure X-ray spectra with unprecedented precision and test quantum electrodynamics in strong field regimes, but it will also find magnetars whose cooling curves do not match any existing equation of state. Gravitational wave detectors will catch the signals from merging neutron stars and possibly from glitching magnetars, but they will also detect events that do not correspond to any known source. Each new dataset will answer old questions and raise new ones. That is how science works at the frontier. Progress is not linear, it is iterative. You learn something, you test it, you refine it, and you move on to the next puzzle. Magnetars are just one piece of a much larger picture, but they are a critical piece. They are the objects that force us to confront the limits of what we know and push us to build better theories, better models, better instruments. And here is the thing that keeps the field moving forward. We are not done, not even close. The census of magnetars is incomplete. The burst mechanism is understood in broad strokes, but not in detail. The connection between magnetars and FRBs is confirmed, but not fully explained. The role of companions, the possibility of magnetar black hole binaries, the connection to gravitational wave sources, the constraints on dark matter and axion-like particles, all of it is still open. The questions outnumber the answers, and the tools to address those questions are just now coming online. The next decade will not wrap up magnetar research. It will crack it wide open. There is a line in a 2021 paper that framed magnetars as objects that were not meant to exist. The phrasing is deliberate. It captures the tension between what theory predicts and what observations reveal. Theory says magnetars should be rare, should have short active lifetimes, should decay quickly. Observations say they are scattered across the galaxy. They persist for thousands of years, and they flare with energies that rival supernovae. The gap between those two statements is where the science lives, and the gap is closing, slowly, with effort, but it is closing. Every new magnetar discovered, every burst measured, every spectrum analyzed, every simulation run, brings us a little closer to understanding not just what magnetars are, but why they exist in the first place, why the universe builds them, what role they play in the broader ecology of neutron stars and compact objects, whether they are common or rare, whether they are a transient phase in every neutron star's life, or a distinct evolutionary path taken only by a lucky or unlucky few. The philosophical implications run deeper. If magnetars exist, if the universe can build objects this extreme and this stable, then the boundaries of what we consider possible need to be redrawn, not eliminated, redrawn. There are still limits. Black holes are still the densest objects allowed by general relativity. The speed of light is still the cosmic speed limit. Quantum mechanics still governs the behavior of particles and fields, but within those limits, the range of outcomes is wider than we thought. Magnetars prove that. They are objects that sit at the edge of the allowed parameter space, pushing every limit without crossing any. They are, in that sense, a message from the universe. A reminder that reality is not constrained by human expectations. It is constrained only by the laws of physics, and those laws, while strict, are also generous. They allow for far more strangeness, far more complexity, far more extremity than we have historically given them credit for. That is the lesson Magnetars teach. Not that the impossible becomes possible, but that the boundary between the two is blurrier than it looks, and that exploring that boundary, poking at it, testing it, measuring it, is not just scientifically valuable, it is necessary, because the universe has already explored it. It has already built the objects. They are out there, spinning in the dark, flaring without warning, bending space-time and polarizing the vacuum and storing more energy in their magnetic fields than most stars will produce in their entire lifetimes. We did not predict them. We did not design them. We did not ask for them. They exist anyway, and they will keep existing long after our telescopes have shut down and our theories have been revised and our understanding has moved on to the next frontier. They do not need us to notice them, but we need them because they show us what the universe is capable of. And the universe, as it turns out, is capable of quite a lot. So here we are, standing at the edge of a graveyard where stars go to die, and what rises from the rubble is not silence, not emptiness, not the clean, predictable decay you expect from something that has run out of fuel and given up. What rises is violence, precision, a clockwork bomb wrapped in a magnetic field so strong it rewrites the rules of light, matter, and empty space itself. A magnetar is 12 miles wide. It weighs more than the sun. It spins once every few seconds, and in a tenth of a second, without warning, it can release more energy than our star will produce over 100,000 years, bright enough to strip atmospheres from planets sitting 10 light-years away, loud enough to be heard across the galaxy. And the only reason we are safe is geography. Distance, the blind luck that there are none close enough to matter. Not yet. We did not predict these things. We stumbled into them. Anomalies in the data that refused to behave. Objects that sat quietly in the catalogue for decades before someone figured out what they actually were. And when the answer came, it was not comfortable. It was not small. It was a magnetic field strong enough to bend space-time, polarize the vacuum, and turn atoms into needles. A field storing enough energy to outlast civilizations. A field that decays not because it runs out of fuel, but because the star itself cannot hold it forever. Black holes hide. Magnetars reveal. And what they reveal is this: the universe, when it wants to, can build weapons. Not with intent, not with malice, just with physics, taken to its absolute limit, pushed until it bends, and the bend, as it turns out, is far stranger than the break. That is the truth Magnetars force us to swallow. The impossible is not